It's hard to get to space. As much as we all wish there were an easy and affordable way to see our planet floating in the dark, right now, the only way is to become an astronaut or a billionaire. But there is a concept that might make it possible while serving as the starting point for the exploration of the universe, the space elevator. How exactly does it work? To understand how a space elevator will get us into space, we must first understand what an orbit is. Being in orbit basically means falling towards something but moving fast enough to miss. If you throw a ball on Earth, it makes an arc through the air and then hits the ground. In space, gravity makes you move much the same way, but if you move sideways fast enough, the curvature of the Earth makes the ground fall away beneath you as fast as gravity pulls you towards it. So to enter Earth's orbit, rockets have to go up and sideways fast. By contrast, a space elevator taps into energy from the Earth's rotation to get the cargo going fast. Imagine a child spinning a toy on a rope with an ant on the child's hand. As the ant climbs out along the rope, it starts to move faster and faster as it ascends. Compared to rockets, with cargo launched on an elevator, you only need to provide the energy to go up. Fast sideways movement comes free with the Earth's rotation. But a space elevator would, without a doubt, be the single largest and most expensive structure ever built by humans. So, is it worth it? It all comes down to costs. Rockets burn a huge amount of rocket fuel just to get a small amount of cargo into space. At current prices, it costs about $20,000 to put 1 kilogram of payload into space. That's $1.3 million for the average human, $40 million for your car, billions for an international space station. This immense cost is one of the major limitations of human spaceflight. Even with advancing technology, this cost isn't likely to be comparable with the price of an airline ticket anytime soon. A space elevator would solve this problem. After construction, a space elevator is projected to reduce the cost 100-fold to $200 per kilogram. If an inexpensive space elevator costs $20 billion, then we'll recoup our losses after launching only 1,000 tons. Close to the weight of 2 international space stations. So what would a space elevator look like in real life? A space elevator has 4 major components: the tether, anchor, counterweight, and climber. The elevator part of the space elevator is the tether and the climber. It extends from the surface of the Earth to space. The climber is like a conventional elevator carriage, a chamber that works its way up and down the tether. At the base would be an anchor, pinning the tether to the Earth, along with a port for climbers. At the top is the counterweight, which holds up the tether. The tether is held tight like a rope and supported from above by the tension from the counterweight, located higher than 36,000 kilometers above the Earth's surface. At the counterweight could be a space station, a launching point for all missions from the spaceport elevator. But can we actually build one? It's hard to say. The biggest challenge is the tether. It needs to be light, affordable, and more stable than any material we can produce right now. There are promising materials like graphene and diamond nanothreads, but even they may not be strong enough. And aside from being incredibly strong, the tether would also have to withstand atmospheric corrosion, radiation, and micrometeorite and debris impacts. Additionally, it takes several days to climb the elevator. How do we power the climber? It requires a lot of energy to go up. Do we need a nuclear reactor on our elevator carriage? Or do we beam it power from the ground with a super-powered laser? And where do we get the raw materials for a 36,000-kilometer long tether? Do we make it on Earth and launch it into space, or do we make it in space and lower it down to the Earth? Could asteroid mining be the answer? Put simply, there are still some major technological hurdles to overcome. And a space elevator is not without risk. Should the tether break, it would collapse in spectacular style. If it breaks near the anchor, the force exerted by the counterweight will cause the entire elevator to rise up, ascending into space. Should it break near the counterweight, the tether will fall, wrapping around the world and whipping the end off. The resulting debris in orbit could pose serious problems to future spaceflight. If we build a space elevator on Earth, we have to do it right the first time. For these reasons, some experts have proposed first building a space elevator on the Moon. The Moon's gravity is much weaker than the Earth's, so a flimsier but existent material like Kevlar could serve as a tether. Even with all these challenges, the payoff of having a working space elevator would be immense. It might be the first step to truly becoming a spacefaring civilization. Maybe we will never build a space elevator, but in trying to do so, we might learn an awful lot. And when it comes to the exploration of the universe, there can't be too many dreams of a glorious future. Black holes are the most powerful and extreme things in the universe, and they're wildly weird and complicated. What would happen if you fell inside one, and what are they really? First, we need to talk about space and time. Space and time are the grand stage where the play of the universe unfolds. But space isn't a fixed stage, and time doesn't tick the same for everyone everywhere. In short, they're relative. Matter bends space, and bent space tells matter how to move. Put some stars and planets on the stage, and it sags underneath them. That misshapen stage, with all its little warps and dips, gives us gravity. Black holes do not just bend the stage, they're like trapdoors, places with so much mass that the universe formed a no-go zone where the rules change. Most black holes form when very massive stars die. We explained this process in detail in our neutron star video. All you need to know now is that in the final moments of really massive stars, their insides implode at nearly a quarter of the speed of light. This packs so much mass so close together, creating something so dense that it sort of breaks the stage of the universe. A black hole with 10 times the mass of the Sun would be barely 60 kilometers across. If you look directly at a black hole, it looks like nothing. The space under their control is blocked by an invisible, one-way border called the event horizon. The event horizon forms a shell around a region of space that, once entered, is shielded from the rest of the universe forever. Because the black hole trapdoor deforms space so much, not even light can escape it. And with nothing escaping to transfer information from the inside, it's impossible to tell what it really looks like. We can still observe black holes because of their effect on matter. Things can orbit black holes just as they can orbit the Sun or a planet. Many black holes have disks of matter orbiting outside the event horizon. This matter can become incredibly hot, as close orbits can speed this matter up to half the speed of light, and tiny amounts of friction and collisions between particles heat them to 1 billion degrees, making the space around these black holes, ironically, incredibly bright. What would happen if you were to try to get close or even inside a black hole? First of all, you'd see the strangest funhouse mirror in the universe. Matter isn't the only thing orbiting a black hole. Gravity is so strong near them that light can orbit too. If you hovered just outside the event horizon, at the photon sphere, in any direction, you just see yourself. Straight ahead would be the back of your own head, as light from your back travels around the black hole to your eyes. Gravity also alters the passage of time itself. The stronger the gravity, the slower time passes. While you watch the universe above you speed up, those far away will watch you in slow motion. If you chose to fly away from the black hole, you might find that eons have passed for the rest of the universe, a freakish one-way time travel trip to the future where your loved ones are long dead. But getting close to a black hole can be incredibly dangerous. A painful death by spaghettification awaits you. Because your feet are closer to the black hole than your head, they feel a stronger pull of gravity, enough to pull you apart. As you descend, it gets worse. The pulling gets stronger, your body squeezed thinner and straighter until you've been reduced to a thin stream of hot plasma, gobbled up in one final slurp, never to be seen again. Spaghettification is only a risk with smaller black holes since they have much smaller radii. If you go to the center of a galaxy and find a supermassive black hole, you might be able to experience crossing the event horizon. As you approach the event horizon, a distant observer would think they never saw you enter it, seeing you stop and fade. The last light you emit trickling up and out away from the event horizon. Meanwhile, from your perspective, the void of the black hole rises up to meet you as light from fewer directions can reach you. The blackness envelops you until your only view of the universe you left is a tiny spot of light. Here, inside the event horizon, space and time are so horribly broken that real time travel is possible, so it's probably a good thing that nothing gets out. If anything could escape, it could create all sorts of time travel paradoxes and issues that break the universe. As scary as the event horizon is, it keeps us safe from that drama. Whether you have survived this long doesn't really matter, as now there's only the certainty of crushing death in your near future. Inside the event horizon, space-time itself is so bent and warped that whatever direction you move here, every forward you go leads only towards the center of the black hole. Trying to go in any direction only brings you to the center faster. To survive the longest, you must do nothing. In the center of the black hole, we find the singularity, a single point with all the matter that has ever crossed the event horizon, all crushed to a point infinitely small. There is no memory of the things that made it, as stuff disappears down the black hole trapdoor forever. The singularity makes all things equal. This actually breaks the universe in really cool ways. We've made a video about this problem if you want to learn more. But in a nutshell, everything that comes too close becomes black hole matter concentrated at the singularity. This lack of a memory of its past means that a black hole has only three properties: its mass, spin, and electric charge. Everything else is lost. They're a lot like fundamental particles in that respect. This actually means that every single black hole in the universe is the same. Sure, their mass is different and some spin faster than others, but if we were to put all the singularities into a magical physics museum, they'd be identical, like electrons. But just like fundamental particles, the properties of singularities are the best ways we can describe them on paper, rather than an accurate representation of reality. Our current theories about the universe, namely general relativity, are just not able to describe or explain them. The curvature of space becomes infinite, density becomes infinite, and our rules just don't make sense. The singularity has no surface or size, something like a divide by zero error in the universe. So singularities might not even exist, or be completely different things. But this is all we know right now from the best prediction we have from our best current theory of space-time. Also, basically everything you've ever heard about black holes, even in this video, is about theoretical black holes that aren't spinning because their maths is so much easier. But since black holes were born from dying stars that were spinning extremely quickly in their final moments, as far as we know, all black holes in the universe should be spinning right now. At incredible speeds too, up to 90% of the speed of light. This means that in reality, black holes are even more screwed up than they usually get credit for. The singularities of rotating black holes are even wilder. The rotation causes them to swell outwards into a sort of ringularity. This rotation is so powerful that space itself is dragged along. This creates another region around spinning black holes called the ergosphere, where it's impossible to stay still no matter how hard you try. Like a rushing whirlpool of space-time, the tide is irresistible, and the black hole makes you orbit it whether you want to or not. Okay, so what will happen to black holes as the universe ages and dies around them? Again, we don't know, but we have some ideas based on our current understanding of physics. Hawking radiation. In quantum field theory, the vacuum of space is boiling with quantum fluctuations. These fluctuations are creating matter and antimatter pairs of particles from nothing which only exist for a very short time before annihilating. When this happens near the event horizon of a black hole, one of these particles can fall in, stopping them from annihilating. The escaping particle is Hawking radiation. Ultimately, the mass of this particle must come from the black hole, so over eons, black holes will shrink and radiate away. Hawking radiation is not the stuff that fell into the black hole, it's new stuff, stealing mass from it. As the black hole shrinks, the Hawking radiation gets stronger, faster and faster, until what's left eventually evaporates in a flash of high-energy radiation like a nuclear bomb. And then, nothing. But that won't happen for a long time. A black hole with the mass of our Sun has a lifetime of 10 to the power of 67 years. Which means that it would take 10,000 billion years to lose 0.0000001% of its mass. But most black holes are way more massive than our Sun. The most massive supermassive black holes in the centers of galaxies have lifetimes of 10 to the power of 100 years. How long is that? Imagine an hourglass filled with 1 grain of sand for every single particle in the universe. Every 10 billion years, 1 single grain of sand falls to the bottom. If we waited for all the sand to fall down, not even 1% of the lifetimes of these black holes would have passed. There is no good concept to help our brains grasp these timescales. Will we ever truly understand black holes? Really know what's going on inside them? No one knows. We can only see their outsides, and the theories we have probably get their insides wrong. But it's okay to not know everything. It just means there's still work to be done. It means there are still mysteries to solve and big ideas to think about, which is why humans do science. In the end, we can at least be sure that we still have plenty of time left to think about them before the last one melts away. Space travel is the most exciting and challenging adventure humanity has ever undertaken. But in an irony of history, we may stop ourselves from going into space the more we do it. With every rocket launched and with every satellite deployed, we're creating a trap for ourselves that gets deadlier and more dangerous every year. If it's ever activated, it could end the space age and trap us on our planet for decades or even centuries. Getting something into space is incredibly hard. To do so, you need to move very, very fast, at first straight up to leave the atmosphere, then sideways to begin a sort of circling around the Earth, still very, very fast. If you do that successfully, you can enter a low Earth orbit. And once in orbit, it's very hard to get out of orbit. Unless you have energy to spare, you're sort of locked in here, falling around the Earth forever. That's great for things we want to stay up, like space stations and satellites. And so we moved the majority of humanity's space infrastructure to this place, just a few hundred kilometers above the surface. Just high enough so that the atmosphere is so thin that orbiting things can stay up for centuries before air resistance can slow them enough to bring them back to Earth. But this is also the source of our deadly trap. Rockets are really metal cylinders that keep big piles of fuel in place. Whenever a portion of the fuel has been spent, the empty tanks are dropped to make the rocket lighter. Some parts crash down to Earth or burn up in the atmosphere, but most of the useless rocket parts stay up and begin to orbit the planet. After decades of space travel, low Earth orbit is a junkyard of spent boosters, broken satellites and millions of pieces of shrapnel from missile tests and explosions. Right now, we know of around 2,600 defunct satellites, 10,000 objects bigger than a monitor, 20,000 as large as an apple, 500,000 pieces the size of a marble, and at least 100 million parts so small they can't be tracked. This debris is moving at speeds of up to 30,000 kilometers per hour, circling Earth on crisscrossing orbits multiple times a day. Orbital speeds are so fast that being hit by debris the size of a pea is like being shot by a plasma gun. On impact, the debris vaporizes, releasing enough energy to punch holes straight through solid metal. So, we've covered the space around our planet with millions of deadly pieces of destruction. And we also put a $1 trillion global infrastructure network right in the danger zone. It performs critical duties essential to the modern world: global communication, GPS and navigation, collecting weather data, looking out for asteroids, and all manner of scientific discoveries. Things we would miss very much if they suddenly went away. If just one pea-sized bullet hits one of our 1,100 working satellites, it will be destroyed instantly. 3 or 4 satellites are already being destroyed this way every year. As the number of satellites and the amount of junk in orbit is expected to grow tenfold in the next decade, we're approaching a tipping point. But the worst thing in space is not tiny pieces of junk. The worst thing would be an unstoppable chain reaction that turns a lot of non-junk things into junk. For example, if two satellites hit each other in just the right way. If satellites collide, they don't stop and fall out of the sky. It's more of a splash than a crash. Orbital speeds are so fast, solid pieces spray right through each other, transforming the two satellites into clouds of thousands of little things still fast enough to destroy more satellites. This could trigger the slowest and most destructive sort of domino effect, a collision cascade. Like a shotgun spray, each collision creates more bullets. What was once a single tiny target, very unlikely to hit anything, becomes a wall of destruction, hungry to make more. As more and more satellites are destroyed, the destruction accelerates exponentially, eventually destroying everything parked in orbit. But space is very empty, so the first few collisions may take a long time. By the time we realize what's happening, it's too late. 1 year, 1 satellite is destroyed, and that's no big deal. The next year, 5. The year after, 50, until there's nothing left. The situation in orbit is rapidly worsening, and we may already be past the point of no return. Within 10 years, space around Earth may no longer be viable for long-term satellites or rockets. The worst-case scenario is horrifying. A debris field made of hundreds of millions of pieces, many too small to track, moving at 30,000 kilometers per hour. It would effectively create a deadly barrier around Earth, possibly too dangerous to cross. Dreams of moon bases, Mars colonies, or space travel at all may be set back centuries. And the loss of our space infrastructure would send some of the technology we rely on daily back to the 1970s. But it might not be too late to clean up our mess. While the space industry has become better at avoiding space junk, it's still growing fast and occasional weapon tests don't help. So there have been a couple of wild but also serious suggestions about how to quickly remove as much deadly space junk as possible without creating more in the process. Lots of ideas are being thrown around, and some of the most seriously considered involve capture and return missions, which are being tested now. One method involves meeting a piece of junk in orbit with a small satellite loaded with a net. Once caught, a small rocket could be used to bring it down towards Earth. Targets too large for a net might be instead caught with a harpoon on a tether. Instead of firing a rocket, the cleaner would deploy a large sail to produce atmospheric drag and accelerate orbital decay. And there are lots of other wild sci-fi sounding proposals too. Some might use giant electromagnets. These magnetic tugs work by pushing on the magnetic components inside satellites that they use to stabilize and orientate themselves in Earth's magnetic field. These may be safer and more reliable than nets and harpoons because they never have to make contact with the junk they're handling, so there's no risk of accidentally breaking up their target into more junk. As for the tiniest bits of junk, lasers might be the key to vaporizing them entirely. Satellites with lasers wouldn't need to visit their targets, they can shoot them from far away. Large objects can't exactly be shot down, but lasers can be used to ablate them or burn tiny amounts of material off the side to push the junk to a safer orbit. Whatever technology we use in the end, we better start doing something soon, before 100 million bullets become a trillion and the trap is set. If we don't act, our adventure in space might end before it's even begun. From hostile deserts to lonely islands and the highest mountains, wherever there is space to expand into, humans do so. So it's hardly surprising that we're already making preparations to set foot on Mars and to create the first permanent colony outside of Earth, maybe even terraform another planet and turn it into a second blue home. But wait, before we can get to the nice future stuff, we first have to complete the second phase of colonization, creating a semi-permanent outpost to prepare the ground for a larger human presence. But doing so will be gruesome. Even for an expansionist species like us, Mars is extreme. At first glance, Mars seems familiar. Polar ice caps, large valleys, liquid water under its surface, and a day barely longer than Earth's. The ideal place for us to go. Unfortunately, Mars is actually a cold, radioactive desert where the ground is poisonous and breathing is impossible. Mars is awful. You almost certainly don't want to go there. The pioneers doing the hard work on Mars will have an intensely stressful life filled with incredibly challenging problems never encountered before. But there are plenty of people willing to do that work, and we have the technology to enable them to do it. For this video, we will assume there have been prior missions to Mars to scout out a good place for an outpost, store resources and equipment, and that there's already a moon base that serves as a hub for Mars missions. The first major challenge for our outpost is the fact that Mars is very energy poor. Because of its distance from the Sun, solar power is only 40% as effective as on Earth. But even this weakened sunlight is often obscured for days by enormous dust storms. Solar power alone will probably not be enough. Alternatives such as wind power and geothermal energy are also unfeasible, as there's hardly any atmosphere and Mars's interior is much too cold. Initially, nuclear technology might be the only option. Since Mars doesn't have easily accessible radioactive elements, the nuclear fuel needs to come from Earth along with the reactor. If we do set it up, it could power our small outpost for the first few years. Unfortunately, all that energy won't be very useful if we can't breathe. Mars's atmosphere is only 1% as dense as Earth's and mostly made up of CO2. So our habitats need to be pressurized and filled with an artificial atmosphere made of nitrogen and oxygen, which comes with more problems. Corners and flat walls are weak points, so the habitats will have rounded and smooth shapes to handle the stress of great pressure differences between the interior and exterior. The airlocks need to be very airtight and work perfectly every time. Without an extensive magnetosphere or a dense atmosphere, half of all radiation coming from space reaches the ground. A person on the surface would be subjected to 50 times the radiation that they would be on Earth. 3 years on the surface of Mars exceeds the radiation dose limits imposed on NASA astronauts for their entire career. This increases cancer risks significantly. To prevent that, we could shield our habitats with a thick layer of frozen CO2 that can be harvested directly from the atmosphere. Covering the dry ice with a meter of dirt would further increase the level of protection. Sadly, this means almost no windows. From the inside, most living spaces will be windowless tunnels. From the outside, they'll look like burial mounds. All of this would still not hold back all the radiation, but reduce it just enough to be survivable for long periods of time. It won't, however, protect anyone who ventures outside. So remote-controlled robots will be used for routine work on the surface while our crew stays inside. Staying inside is a good idea for another reason: Mars dust. It's much finer than dust on Earth, so it could find its way into the gears or electronics of our machines. Because it's also very dry, it's electrostatically charged, sticking to everything, like spacesuits. It would be impossible to avoid carrying lots of Mars dust into our habitat and into the lungs of our crew. To make this even worse, Mars's soil is filled with very toxic perchlorate salts. Constant exposure could be deadly. This problem can still be overcome though. Spacesuits, for example, could be made in a way that they never truly enter the base but stay attached to the outside of the habitats. Okay, great. Now we've safely isolated humans in terms of energy and air and protected them from cancer, we just need to feed them. Water is easy to come by if a settlement is positioned near the Martian poles with their thick layers of ice. Growing food is a different kind of challenge though. Mars's soils are alkaline and lack the vital nitrogen compounds that plants need to grow. Before we can grow anything, we will have to decontaminate the soil, which is difficult and expensive. Then the soil can be fertilized using recycled biological waste. All of this will take a lot of time and is very energy intensive. So we might use aquaponics to raise fish and plants together, making the astronauts' diets more varied and tasty at the same time. This will be an important psychological boost for our overworked crew. All of these things don't solve one fundamental problem though. Mars has only 38% of Earth's surface gravity, which could cause muscle wasting, bone loss, and cardiovascular problems. While this might be solved in the future by setting up rotating living spaces, for now our crew has to live with low gravity and exercise a lot to slow the degradation down. The crews will probably have to rotate every few years. after being stuck indoors in tight spaces without windows, with the same people, performing the same routines day in, day out, with little contact from the outside world and a lot to worry about. Like Antarctic scientists or submarine staff, they will undergo intense psychological screening to make sure they're mentally resilient enough to handle this lifestyle for several years. Establishing the first real infrastructure on Mars will be extremely taxing work that only a group of very determined and competent people can do. Luckily, we have enough of these on Earth. And there you have it, a small Mars base that will survive for at least a few decades, as long as it's getting a constant supply of resources, parts, nuclear fuel, and crews from Earth. Unfortunately, Mars and Earth are separated by millions of kilometers and orbital periods that leave only a narrow travel window every 2 years. If there's an emergency in the colony, Earth wouldn't be able to help until the next travel window opens. Helpers may arrive on a planet filled with corpses. Settling Mars will be the toughest challenge we have ever faced. It will be gruesome work to establish the infrastructure we need. But we're stubborn and we like extreme challenges. If we push through Phase 2 of colonization, anything is possible. Cities illuminating the dark Martian night, a hub for travel between the planets, industries setting foot in orbit, terraforming, a true multi-planetary future. Going to Mars is hard, but worth it. And if we're lucky, we might be around long enough to see it happening and cheer on the people who take on these challenges for the benefit of us all. The Solar System. Our home in space. We live in a peaceful part of the Milky Way. Our home is the Solar System, a 4.5 billion-year-old formation that races around the galactic center at 200,000 kilometers per hour and circles it once every 250 million years. Our star, the Sun, is at the center of the Solar System. It's orbited by 8 planets, trillions of asteroids and comets, and a few dwarf planets. The 8 planets are divided into 4 planets like ours: Mercury, Venus, Earth, and Mars, and 4 gas giants: Jupiter, Saturn, Uranus, and Neptune. Mercury is the smallest and lightest of all the planets. A Mercury year is shorter than a Mercury day, which leads to enormous fluctuations in temperature. Mercury does not have an atmosphere or a moon. Venus is one of the brightest objects in the Solar System and by far the hottest planet, with atmospheric pressure that is 92 times higher than on Earth. An out-of-control greenhouse effect means that Venus never cools below 437 degrees Celsius. Venus also doesn't have a moon. Earth is our home, and the only planet with temperatures that are moderate enough to allow for a surplus of liquid water. Furthermore, it's so far the only place where life is known to exist. The Earth has 1 moon. Mars is the second smallest planet in the Solar System and hardly massive enough to keep a very thin atmosphere. Its Olympus Mons is the largest mountain in the Solar System, more than 3 times as high as Mount Everest. Mars has 2 small moons. Jupiter is the largest and most massive planet in the Solar System. It consists largely of hydrogen and helium and is the theater for the largest and most powerful storms we know. Its largest storm, the Great Red Spot, is 3 times as large as Earth. Jupiter has 67 moons. Saturn is the second largest planet and possesses the smallest density of all the planets. If you had a sufficiently large bathtub, Saturn would swim in it. Saturn is also known for its extended, very visible ring system. It has 62 moons. Uranus is the 3rd largest planet and one of the coldest. Of all the gas giants, it's also the smallest. The special thing about Uranus is that its axis of rotation is tilted sideways in contrast to the 7 other planets. It has 27 moons. Neptune is the last planet in the Solar System and is similar to Uranus. It's so far removed from the Sun that a Neptune year is 164 Earth years long. The highest wind speed ever measured was in a storm on Neptune at just under 2,100 kilometers per hour. Neptune has 14 moons. If we compare the sizes of the planets, the differences between them become even clearer. Jupiter is the leader in terms of size and weight. Small Mercury, on the other hand, is even smaller than one of Jupiter's moons, Ganymede. Jupiter is so massive that alone it contains roughly 70% of the mass of all the other planets and has a massive impact on its surroundings. That's a blessing for Earth, since Jupiter draws most of the dangerously large asteroids that could wipe out life on Earth. But even Jupiter is a dwarf in comparison to our star, the Sun. Calling it massive does not do justice to the Sun. It makes up 99.86% of the mass in our solar system. For the most part, it consists of hydrogen and helium. Only less than 2% is made up of heavy elements like oxygen or iron. At its core, the Sun fuses 620 million tons of hydrogen each second and generates enough energy to satisfy mankind's needs for years. But not only the 8 planets orbit our Sun, trillions of asteroids and comets also circle it. Most of them are concentrated into 2 belts: the asteroid belt between Mars and Jupiter, and the Kuiper belt at the edge of the solar system. These belts are home to countless objects, some as large as a dust particle, others the size of dwarf planets. The most well-known object in the asteroid belt is Ceres. The most well-known objects in the Kuiper belt are Pluto, Makemake, and Haumea. Usually, we describe the asteroid belt as a dense collection of bodies that constantly collide. But in fact, the asteroids are distributed across an area that is so indescribably large that it's even difficult to see 2 asteroids at once. Despite the billions of objects in them, the asteroid belts are fairly empty places. And nonetheless, there are collisions over and over again. The mass of both belts is also unimpressive. The asteroid belt has a little less than 4% of our Moon's mass, and the Kuiper belt is only between 1/25th and 1/10th of Earth's mass. One day the solar system will cease to exist. The Sun will die, and Mercury, Venus, and maybe Earth too will be destroyed. In 500 million years, it will become hotter and hotter until at some point it will melt Earth's crust. Then the Sun will grow and grow and either swallow Earth, or at least turn it into a sea of lava. When it has burnt up all its fuel and lost most of its mass, it will shrink to a white dwarf and burn gently for a few billion more years before it goes out entirely. Then, at the latest, life in the solar system will no longer be possible. The Milky Way will not even notice it. A small part of it, in one of its arms, will become just a tiny bit darker, and mankind will cease to exist, or leave the solar system in search of a new home. There might be an object so indestructible, extreme, and brutal that it could kill black holes, gravastars, cosmic soap bubbles filled with pure energy and with a shell made of the weirdest material that's possible in nature. What are they? What do they look like? And are they just a theoretical fever dream, or will they change our understanding of the universe forever? The birth of the most extreme objects in the universe. Very massive stars die in the most dramatic way possible, a supernova. We've explained this process in detail before, but in a nutshell, in less than a second, their cores collapse, crushed under their extreme gravity. The star's shell rushes in, bounces against the collapsing core, and explodes, shining brighter than whole galaxies. Depending on how massive the star was, there are 2 possible outcomes. Either the core compresses into a super-dense neutron star, or it kind of breaks reality and collapses into a singularity, an infinitely dense point with no size or dimensions at all. A place where the laws of the universe stop making sense and time and space are reversed. A black hole. Gravastars are a third, even weirder option. Instead of collapsing into an infinitely dense point, the core is kind of ground down, like a rock pulverized to dust by a cosmic hydraulic press. Atoms and particles are crushed so hard that they transform into pure energy. A sort of mini-universe, if you want. And just like our universe, this bubble violently wants to expand and grow. In a fraction of a second, the bubble smashes into the collapsing star around it. The unspeakable mass of the star collapsing under its own gravity meets the titanic violence of the expanding energy bubble. Like an ancient god hammering on its anvil, matter is trapped between an immovable object and an unstoppable force, forging a new kind of material that we've never seen before, but that we know is physically possible. And then it suddenly stops. A gravastar is born. What does it look like? Cosmic soap bubbles. Just like black holes, a gravastar can have any mass, but a typical one would be about the size of the London metropolitan area and as massive as 10 suns. The shell of the gravastar is utterly dark and the coldest thing in the universe, only a billionth of a degree above absolute zero. If we look at it in deep infrared, even the cosmic microwave background glows bright in comparison. How can anything made of matter be that cold? Don't all atoms jiggle back and forth? The thing is, the shell's not made out of atoms. It's made from an entirely new, unique and extreme matter that doesn't have a name yet, and that's at the very limit of what's physically possible in nature. Actually, the shell is so incredibly thin that atoms seem truly gigantic next to it. And yet, despite being ultra-thin, because it's been forged by two impossibly extreme forces, the shell is incredibly tight. So tight that if you wanted to stretch the whole shell by just 1 meter, you'd need the energy of an entire supernova. What about the inside? Well, it only gets weirder. The interior of a gravastar is perfectly simple because it's sort of empty. Completely empty. A perfect vacuum without a single atom, particle, or wave. But despite being as empty as it gets, this vacuum is boiling with the most primitive and fundamental kind of energy in the universe. We need a detour to explain how any of this makes sense. The fundamental nothingness at the core of it all. The inside of a gravastar breaks our brains a bit because it's a sort of supercondensed nothingness. What does this even mean? We'll have to simplify and use metaphors to make sense of what scientists measure and calculate. According to our current understanding of physics, particles like quarks, electrons, photons, and so on are not really solid objects, but sort of waves in an ocean. In our human world, you can't have waves without water, and in the smallest world, you also can't have particle waves without some kind of underlying, omnipresent cosmic fluid. This fluid is the vacuum, what we perceive as nothingness. It's the fundamental ocean at the bottom of reality. The waves of this vacuum ocean are the particles that make up you and everything else. But even when there are no waves or particles traveling through it, the fluid is still there, and like any fluid we know, it has inherent energy. Vacuum fluid is everywhere in the universe. The room you're in is 99.98% vacuum between the air particles bouncing around. Between the trillions of particles making up your cells, there's vacuum. But it's different inside a gravastar. When our star collapsed and condensed so violently, it was as if the universe took a cosmic pump and compressed as much vacuum fluid as physics allows, into a kind of super dense nothingness. As said before, even without any waves, the nothingness vacuum ocean of the universe has energy. But the super dense vacuum inside a gravastar has almost a billion, trillion times more energy per cubic centimeter than the vacuum outside the star. This is an unbelievable amount of energy and mass in a tiny space, just like, you may have guessed it, black holes. This intensely compressed vacuum ocean can't be compressed any further. It's at the absolute physical limit of anything that can be squeezed together without breaking physics, like black holes do. The ocean would love to stop being so tight. It wants to stretch out and flow back into the ocean that surrounds the star, but it's trapped in the safest prison possible. The shell, which itself is right at the edge of the physical limit of any material possible. An eternal stalemate between two limits of the universe. Let's leave this world of metaphors and get back to our world that feels more real. In our world, gravastars are perfectly black, eternal objects with borderline insane amounts of mass. Because they're so cold, dark, and massive, from the outside, gravastars look and behave exactly like black holes. Both massively curve space around them and create all the fun effects we love black holes for, from trapping mass and light in accretion disks or slowing down time as you get closer. For details, we've made 1 or 2 videos on black holes before. If you fell into a gravastar, you'd be extremely dead before you even hit the surface, ripped apart and ground down by the gravitational forces. And once your scattered remains touch the shell, the atoms you were once made of would probably break down and dissolve completely, only to be converted into the vacuum energy of the interior, making the gravastar an infinitesimal bit bigger and an infinitesimal bit more massive. Okay, this was fun and all, but what exactly is the point? Isn't this just another video of wild scientific speculation just for the sake of it? The point. Black holes were suggested more than a century ago as an abstract solution to equations of gravity. For more than 50 years, they were considered mathematically valid, but too absurd to be real. Few believed they actually existed. But scientists kept working on paper and looking at weird things, and then we saw stars being thrown around by invisible titans. We saw light stretching around invisible gaps in the sky, and as our technology and theories improved, we even sort of took a picture of them. We have evidence for them, and they fit our theories. And nowadays, it's kind of common sense to accept them as real. Black holes are extremely elegant and fascinating, but they also created a lot of questions that have traumatized physicists for decades. Singularities literally break our best understanding of physics. They seem to delete information, which shouldn't be possible. Gravastars are a relatively new idea without any of those problems. They don't need singularities that break physics or delete information. They solve the puzzles of black holes, but they too create new problems, like weird exotic matter for their incredibly cold and tight shell, super dense nothing to make a supermassive empty core. But just like black holes, they do work on paper and fit what we see in the sky. So, are they real, and will we ever know? Actually, there is a way to find out. Black holes have an event horizon, while gravastars have a physical shell made of matter, which means that they behave very differently when they smash into each other. The collision of two objects as massive as they are creates huge amounts of gravitational waves, ripples in space-time that travel at the speed of light. You can think of them as the music of cosmic cataclysms. The collision of two black holes should sound like a bass drum, a deep thump that stops quickly. But two gravastars colliding should sound like a gong, leaving subtle echoes behind. Scientists are listening for these echoes in the music of the cosmos. Unfortunately, black holes and gravastars are surrounded by such strong gravity that it swamps most of the music. It's like trying to tell two instruments apart through a thick wall of concrete. You need very sharp technology for that. While we've made incredible progress in the last few years, we're not quite there yet. So this is where we'll end this story. Gravastars have the potential to answer some of the biggest problems in physics. Or they're just another idea for our discard pile. But this is why we do science. To learn that everything is different to the way we thought it is, until the day we truly understand the nature of reality. Getting to space is hard. Right now, it's like going up a mountain on a unicycle with a backpack full of explosives. Incredibly slow, you can't transport a lot of stuff, and you might die. A rocket needs to reach a velocity of about 40,000 kilometers an hour to escape from Earth. To get to that speed, rockets are mostly containers for fuel with a tiny tip of payload. This is bad if you want to go to other planets because you need a lot of heavy stuff if you want to survive and maybe even come back. So is there a way to get to space with less fuel and more payload? A nice thing that solved most of our transport problems on Earth is what you call infrastructure. Whether it's roads for cars, ports for ships, or rails for trains, we've made it easier to get to places. We can apply the same solution to space travel. Space infrastructure will make getting into orbit and out to the Moon, Mars, and beyond easier and cheaper. Great, but what exactly is space infrastructure? Unlike an Earth space elevator, which is currently science fiction, there is a simple yet promising technology that does not require new science, magic materials, or huge investments, and that has been tested successfully in orbit already. A cable and a weight, known as a tether. The concept is so simple, it's surprising. What if we put tethers, hundreds or thousands of kilometers long, into space and had spacecraft use them as ladders to climb to higher altitudes and gain speed? This concept is known as the Skyhook. It works even better if we make it spin. A counterweight holds a long cable in place while it rotates around a circle. A rotating tether slows down its tip relative to the ground at the bottom and speeds it up at the top like a catapult. This means that you can transfer energy from the tether and get a massive boost when released, more or less for free, equal to twice the tether's rotation velocity. Specialized fibers already exist that can survive the extraordinary stresses a Skyhook would be faced with. To protect against cuts and collisions from debris and meteorites, we can thread our tether into a web of redundant fibers. Since our Skyhook would pass over the same spot many times a day, this would allow small, reusable shuttles to catch up with it. Of course, it's not that easy. At its lowest point, the tether's tip is dashing through the atmosphere at around 12,000 kilometers per hour. Because of Earth's atmosphere, we can't lower the Skyhook too much or it will get too hot from air friction. So it will dip to a height of 80 to 150 kilometers and no lower. To match this, we'll need specialized spacecraft that can get to the tether. While this isn't exactly easy, it's still much cheaper than getting a big tin can filled with rocket fuel to go 40,000 kilometers an hour. Catching the tip will be a challenge too. There's only a short time window of 60 to 90 seconds to find a tiny thing in the sky moving at Mach 12. To make this easier, the tip could have a sort of fishing line, a kilometer long, with a navigation drone that helps the spacecraft connect. Another challenge is keeping our Skyhook in orbit. As more and more ships latch onto it and pull themselves up, they use up the momentum that keeps it in place. If we don't do anything, it will slow down and crash into the atmosphere. And here, we can cheat the universe a bit. The Skyhook is a battery of orbital energy. It's possible to balance the payloads coming in and being sent off. Arriving ships bringing humans and materials home to Earth add energy to the tether, which it can give to other ships departing into space. This way, the tether doesn't lose any energy. The more we use it, the cheaper it gets. If we're still losing energy with each boost, we can recover it with small electric or chemical engines that regularly correct the tether's position. A set of tethers, one around Earth and one around Mars, could make trips between the planets fast, straightforward and low cost compared to rockets. The Earth tether would sit in low Earth orbit to grab people and payloads and fling them off to Mars. The Mars tether catches them and slows them down for a landing on the surface. In the opposite direction, the tether could pick up a vehicle traveling through Mars's thin atmosphere at only about 1,000 kilometers an hour, not much faster than our airliners on Earth, and fling it back to Earth to be caught and lowered down. The tethers could shorten trips between both planets from 9 months down to 5 or even 3, and reduce the scale of the rockets required by between 84 and 96%. Even better, people may be able to travel in relative luxury as we could afford to invest in passenger comfort. Tether travel would be first-class seats to Mars. Together, tethers around Earth and Mars could provide the rapid and cost-efficient transportation backbone that would make space travel affordable. But let's go further. Starting from low Mars orbit, a tether could boost ships to the asteroid belt. The first craft sent to a new asteroid would need rockets to slow down at its destination. Subsequent arrivals might find a tether waiting to catch them and send them back for free. Getting to asteroids cheaply is a major factor in opening up the resources of the solar system. Precious metals and valuable minerals could be delivered to Mars just weeks after they were cut out of their asteroid. They would be the perfect building blocks for our interplanetary civilization. But why stop here? Mars moons are very convenient. No other moons in the solar system orbit that close to their planet. Phobos is so heavy that we don't need to worry about slowing it down, making it the perfect attachment point for super tethers just under 6,000 kilometers long. The lower tip would fly just over the surface of Mars and be very easy to catch. The upper tip can fling ships all the way to Jupiter and Saturn. The same super tether can also bring the inner solar system closer. Venus and Mercury are a single swing away. Unlike Mars, they're bursting with solar energy and are rich in minerals. In the long term, nothing is stopping humanity from constructing a zero-propellant transport network for the terrestrial planets centered on the Martian moons. Tethers are a comparably cheap and sustainable solution to making space travel affordable and the rest of the solar system accessible for exploitation and exploration. Considering that we have the technology to build them today, there's really no good excuse to wait any longer. Parts of the solar system are far away, but they could be very close. Today, we are answering an age-old, very scientific and important question. What if the moon crashes into Earth? It's more interesting and weird than you probably think. Let's start with the basics. Why isn't the moon on its way to crash into us already? We know that Earth's gravity pulls everything towards it, including the moon, but somehow it stays up, as if suspended by some opposite force. But there is no other force countering gravity. Instead, the trick to staying up is a sideways motion that we call an orbit. You see orbits every day. When you throw a ball, it makes a tiny little orbit. The only difference between the ball's orbit and the moon's is that the ball eventually hits the ground. Basically, the reason is speed. If you could throw your ball fast enough, it would bend around the world and come back to you. If there were no air slowing it down, it could orbit forever. And this is what the moon does, falling sideways around Earth very fast with no air slowing it down, orbiting Earth every 27 days at 3,600 kilometers an hour. So, for the moon to just stop in its orbit and plummet to the Earth would break more laws of physics than we have time to explain. So, how do we crash it into Earth? In a nutshell, to change an object's orbit, you need to change its speed, which changes where gravity takes it. But even small changes require enormous forces, which is why all the large objects in the solar system are so stable nowadays. According to science, the moon is big and very massive. Even igniting billions of rocket engines all over its surface would barely move the moon. It looks like nothing short of magic will make the moon fall, so we'll use a magic spell that slows down the moon so much that it changes its orbit and spirals towards Earth. To get the most from the experience, the moon will take exactly 1 year before it hits Earth. Ready? 3, 2, 1. Magic. Month 1. For the first few days, nothing really changes. The moon gets a tiny bit brighter and scientists get confused, but the rest of us don't notice anything different. The only noticeable real effect of the moon on the Earth are the tides. Tides exist because while Earth pulls on the moon's gravity pulls back on the Earth. Since the strength of gravity gets weaker with distance, different parts of the Earth feel a slightly different pull, which causes the Earth, especially the oceans, to bulge when the moon is above them and contract a little on the sides when it's not. As Earth rotates every day underneath the moon's influence fluctuates, causing the water level of the oceans to rise and fall by about half a meter twice a day. But with the moon drawing ever closer, high tide gets higher every day. At first barely noticeable, within a month the moon has covered half the distance to the Earth and ocean tides have grown to 4 meters. Every day high tide comes and waves flood coastal cities. And there's no end in sight. With the moon drawing ever closer, tides rise ever higher, inundating another city and more inhabited land with salty water every day. Month 2. By the end of month 2, the moon has covered 2/3 of the distance to Earth and global infrastructure is crumbling as tides rise above 10 meters, displacing up to 1 billion people who happen to live near the coastlines. As ports become inoperable, shipping grinds to a halt. Not only will it slow down the delivery of Kurzgesagt products, but also less exciting things like food. Global communications fall into disarray. 95% of the internet is carried by ocean-crossing cables, and while these largely don't mind the water, their terminals on land do. Living inland doesn't guarantee safety either. Tidal bores cause rivers to flow backwards, carrying salt water to contaminate surface and groundwater supplies. Gas shortages follow as oil refineries near the coast are abandoned. Countries are left with the supplies they had on their shelves, and strict rationing will begin. In the cities, chaos reigns during the scavenging hours of low tide, while survivors take refuge in high-rises when the water returns. Month 3. 3 months in, and the Moon is close enough to disrupt communication and navigation satellites. While it's normally far too distant for its gravity to cause any major problems for our satellites, the closer it gets, the more warped their orbits become. As their fuel for orbital corrections runs out, satellites careen out of control. Months 4 and 5. On Earth, the tides are rapidly growing to about 30 meters and will be reaching 100 meters in height in a few short weeks. At low tide, the ocean recedes hundreds of kilometers, exposing the continental shelf like vast deserts, while at high tide, walls of water drown agriculture, houses, and skyscrapers. And now, almost 5 months in, the apocalypse has finished its warm-up act. Since the oceans are on average only 3 kilometers deep, the tides have reached their maximum. Up until now, the water in the oceans could flow, absorbing most of the Moon's gravitational squeezing, but now the Earth itself is really feeling the squeeze of the ever-approaching Moon. These aren't so much tides of water, but tides of rock. The squeezing of the planet, combined with the weight of quintillions of tons of water sloshing on and off the tectonic plates, creates enormous stresses below and begins to cause earthquakes of increasing magnitude and intensity. It's impossible to say how serious these earthquakes might be or where they occur, but like a child jumping on their bed until it breaks, no good can come of it. Strong tidal forces lead to volcanism on other planets and moons. On Earth, squeezing the planet disrupts the magma reservoirs inside the crust, triggering sizable, climate-altering eruptions in Chile, New Zealand, Yellowstone, and elsewhere. Meanwhile, watching patiently above is the Moon. Still no bigger in the sky than a small cloud. Within 75,000 kilometers of Earth, it is bright enough to illuminate the night sky like twilight. Months 6 and 7. After half a year, the Moon is entering the space once occupied by geosynchronous satellites, where it orbits Earth every 24 hours. It appears to float at one spot in the sky, unmoving, cycling through a full set of phases every day, but only visible to half the planet. With the Moon stationary above the Earth, the tides seem to freeze in place. Half the world flooded, half with its water seemingly returned to the sea, as if Earth is holding its breath to prepare for the worst. As the Moon sinks further, you might wonder if its gravity would overpower Earth's, pulling you up and ending your misery. Fortunately not. The Earth's surface gravity is about 6 times stronger than the Moon's, so even if the Moon were hovering right on top of you, you would still stay on the ground. On the Moon, things are different though. The near side of the Moon is more strongly affected by Earth's gravity, so during the next few months, it starts to stretch forward towards the Earth into something of an egg, triggering deep moonquakes as the lunar rock flexes and changes shape. Though barely noticeable now, this squish will grow to hundreds of kilometers in a matter of months. Months 8 to 11. At this point, the apocalypse has arrived, and we can summarize the months before the crash as everybody left has a really bad time. The tides sweeping over the Earth slow down and then reverse their direction because the Moon now orbits Earth faster than it rotates. The planet will experience an abundance of earthquakes and volcanism. Massive amounts of volcanic aerosols rise high into the stratosphere, shiny enough to reflect sunlight back into space. What little light gets through is rust red and is periodically diminished by daily eclipses. The result is a rapid global cooling with acid rains and summer snows killing even the hardiest plants. The clock runs out on civilization. Billions have perished while an X-shaped moon is still drawing closer. Let's get ready for the grand finale. Month 12. Finally, at the end of the year, the Moon has reached the Roche limit. That's the point where Earth's gravitational pull on the Moon is stronger than the Moon's own gravity. Things on the lunar surface start falling towards Earth, and by the time it crosses 10,000 kilometers, the entire Moon disintegrates into rubble, smearing itself into a massive ring system around the Earth. Fortunately, the Moon's disintegration means the misery on Earth has ended. No moon means the general apocalyptic nature of things comes to a halt. The oceans recede, flowing off the land one last time. Any survivors are treated to a view of tremendous arches spanning the sky, glimmering in the sunlight, illuminating the night sky more brilliantly than any full moon ever could, while meteor showers of moon dust fill the sky. It's hard to say what happens next, but the tranquility may be short-lived. If too much moon dust rains down, friction heats the atmosphere, possibly boiling the oceans. If not, the enormous shadows cast by the rings, combined with all the volcanic and meteoric aerosols, block even more sunlight, and a period of runaway cooling could begin that freezes much of Earth's surface solid. In any case, at some point people will emerge again, from submarines or bunkers or mountain tops. They will not have a great time before rebuilding civilization, and their success is not guaranteed, but at least they'll be trying to do so with beautiful rings in the sky. What is the largest star in the universe, and why is it that large? And what are stars anyway? Things that would like to be stars. We begin our journey with Earth, not to learn anything, just to get a vague sense of scale. The smallest things that have some star-like properties are large gas giants or sub-brown dwarfs, like Jupiter, the most massive planet in the solar system, 11 times larger and 317 times more massive than Earth, and more or less made of the same stuff as our Sun, just much less of it. The transition towards stars begins with brown dwarfs, failed stars that are a huge disappointment to their mums. They have between 13 and 90 times the mass of Jupiter. So even if we took 90 Jupiters and threw them at each other, although fun to watch, it wouldn't be enough to create a star. Interestingly, adding lots of mass to a brown dwarf doesn't make it much bigger, just its insides denser. This increases the pressure in the core enough to make certain nuclear fusion reactions happen slowly and the object glow a little. So brown dwarfs are a sort of glowy gas giant that don't fit into any category very well. But we want to talk about stars, not failed wannabe stars, so let's move on. Main sequence stars. Once large gas balls pass a certain mass threshold, their cores become hot and dense enough to ignite. Hydrogen is fused to helium in their cores, releasing tremendous amounts of energy. Stars that do that are called main sequence stars. The more massive a main sequence star is, the hotter and brighter it burns, and the shorter its life is. Once the hydrogen burning phase is over, stars grow, up to hundreds of thousands of times their original size. But these giant phases only last for a fraction of their lifespan. So we'll be comparing stars at drastically different stages in their lives. This doesn't make them less impressive, but maybe it's good to keep in mind that we'll be comparing babies to adults. Now back to the beginning. The smallest real stars are red dwarfs, about 100 times the mass of Jupiter, barely massive enough to fuse hydrogen to helium. Because they are not very massive, they are small, not very hot, and shine pretty dimly. They are the only stars in the main sequence that don't grow once they die, but sort of fizzle out. Red dwarfs are by far the most abundant type in the universe. Because they burn their fuel very slowly, it lasts them up to 10 trillion years, 1,000 times the current age of the universe. For example, one of the closest stars to Earth is a red dwarf star, Barnard's star, but it shines too dimly to be seen without a telescope. We made a whole video on red dwarfs if you want to learn more. The next stage are stars like our Sun. To say the Sun dominates the solar system is not doing it justice, since it makes up 99.86% of all its mass. It burns far hotter and brighter than red dwarfs, which reduces its lifetime to about 10 billion years. The Sun is 7 times more massive than Barnard's star, but that makes it nearly 300 times brighter with twice its surface temperature. Let's go bigger. Small changes in mass produce enormous changes in a main sequence star's brightness. The brightest star in the night sky, Sirius, is 2 solar masses with a radius 1.7 times that of the Sun, but its surface is nearly 10,000 degrees Celsius, making it shine 25 times brighter. Burning that hot reduces its total lifespan by 4 times to 2.5 billion years. Stars close to 10 times the mass of our Sun have surface temperatures near 25,000 degrees Celsius. Beta Centauri contains 2 of these massive stars, each shining with about 20,000 times the power of the Sun. That's a lot of power coming from something only 13 times larger, but they'll only burn for about 20 million years. Entire generations of these blue stars die in the time it takes the Sun to orbit the galaxy once. So is this the formula? The more massive, the larger the star. The most massive star that we know is R136A1. It has 315 solar masses and is nearly 9 million times brighter than the Sun. And yet, despite its tremendous mass and power, it's barely 30 times the size of the Sun. The star is so extreme and barely held together by gravity that it loses 321,000 billion tons of material through its stellar wind every single second. Stars of this sort are extremely rare because they break the rules of star formation a tiny bit. When supermassive stars are born, they burn extremely hot and bright, and this blows away any extra gas that could make them more massive. So the mass limit for such a star is around 150 times the Sun. Stars like R136A1 are probably formed through the merger of several high-mass stars in dense star-forming regions and burn their core hydrogen in only a few million years. So this means they are rare and short-lived. From here, the trick to going bigger isn't adding more mass. To make the biggest stars, we have to kill them. Red giants. When main sequence stars begin to exhaust the hydrogen in their core, it contracts, making it hotter and denser. This leads to hotter and faster fusion, which pushes back against gravity and makes the outer layers swell in a giant phase. And these stars become truly giant indeed. For example, Gacrux. Only 30% more massive than the Sun, it has swollen to about 84 times its radius. Still, when the Sun enters the last stage of its life, it will swell and become even bigger, 200 times its current radius. In this final phase of its life, it will swallow the inner planets. And if you think that's impressive, let's finally introduce the largest stars in the universe, hypergiants. Hypergiants are the giant phase of the most massive stars in the universe. They have an enormous surface area that can radiate an insane amount of light. Being so large, they're basically blowing themselves apart, as gravity at the surface is too weak to hold on to the hot mass which is lifted away in powerful stellar winds. Pistol Star is 25 solar masses, but 300 times the radius of the Sun, a blue hypergiant aptly named for its energetic blue starlight. It's hard to say exactly how long Pistol Star will live, but probably just a few million years. Even larger than the blue hypergiants are the yellow hypergiants. The most well-studied is Rho Cassiopeia, a star so bright it can be seen with the naked eye, although it's thousands of light years from Earth. At 40 solar masses, this star is around 500 times the radius of the Sun and 500,000 times brighter. If the Earth were as close to Rho Cassiopeia as it is to the Sun, it'd be inside it and you would be very dead. Yellow hypergiants are very rare though, only 15 are known. This means they're likely just a short-lived intermediate state as a star grows or shrinks between other phases of hypergiantness. With red hypergiants, we reach the largest stars known to us, probably the largest stars even possible. So, who's the winner of this insane contest? Well, the truth is, we don't know. Red hypergiants are extremely bright and far away, which means that even tiny uncertainties in our measurements can give us a huge margin of error for their size. Worse still, red hypergiants are solar system-sized behemoths that are blowing themselves apart, which makes them harder to measure. As we do more science and our instruments improve, whatever the largest star is will change. The star that is currently thought to be among the largest we've found is Stephenson 218. It was probably born as a main sequence star a few tens of times the mass of the Sun and has likely lost about half its mass by now. While typical red hypergiants are 1,500 times the size of the Sun, the largest rough estimate places Stephenson 218 at 2,150 solar radii and shining with almost 500,000 times the power of the Sun. By comparison, the Sun seems like a grain of dust. Our brains don't really have a way of grasping this kind of scale. Even at light speed, it would take you 8.7 hours to travel around it once. The fastest plane on Earth would take around 500 years. Dropped on the Sun, it would fill Saturn's orbit. As it evolves, it will probably shed even more mass and shrink down into another hotter hypergiant phase, accumulate heavy elements in its core before finally exploding in a core collapse supernova, giving its gas back to the galaxy. This gas will then go on to form another generation of stars of all sizes, starting the cycle of birth and death again to light up our universe. Let's make this journey again, but this time without the talking. The universe is big. There are many large things in it. If you want to play a bit more with size stuff, we have good news. We've created our first app, Universe in a Nutshell, together with Tim Urban, the brain behind Wait But Why. You can seamlessly travel from the smallest things in existence, past the coronavirus, human cells and dinosaurs, all the way to the largest stars and galaxies, and marvel at the whole observable universe. You can learn more about each object or simply enjoy the sheer scale of it all. The app is inspired by the Scale of the Universe website by the Huang twins that we spent a lot of time with when it came out years ago, and felt that it was finally time to create a Wait But Why and Kurzgesagt version. You can get it in your app store, there are no in-app purchases and no ads. All future updates are included. And since this is our first app, we'd love to hear your feedback so we can improve it over time. If this sounds good to you, download the Universe in a Nutshell app now and leave us a 5-star review if you want to support it. Kurzgesagt and all the projects we do are mostly funded by viewers like you. So if you like the app, we'll make more digital things in future. Thank you for watching. Black holes are one of the strangest things in existence. They don't seem to make any sense at all. Where do they come from? And what happens if you fall into one? Stars are incredibly massive collections of mostly hydrogen atoms that collapse from enormous gas clouds under their own gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing a tremendous amount of energy. This energy, in the form of radiation, pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for stars with way more mass than our own Sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. Unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The core collapses. Within a fraction of a second, the star implodes, moving at about a quarter of the speed of light, feeding even more mass into the core. It's at this very moment that all the heavier elements in the universe are created as the star dies in a supernova explosion. This produces either a neutron star, or if the star is massive enough, the entire mass of the core collapses into a black hole. If you looked at a black hole, what you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling faster than the speed of light to escape. In other words, it's impossible. So we just see a black sphere reflecting nothing. But if the event horizon is the black part, what is the whole part of the black hole? The singularity. We're not sure what it is exactly. A singularity may be infinitely dense, meaning all its mass is concentrated into a single point in space with no surface or volume, or something completely different. Right now, we just don't know. It's like a dividing by zero error. By the way, black holes do not suck things up like a vacuum cleaner. If we were to swap the Sun for an equally massive black hole, nothing much would change for Earth, except that we would freeze to death, of course. What would happen to you if you fell into a black hole? The experience of time is different around black holes. From the outside, you seem to slow down as you approach the event horizon, so time passes slower for you. At some point, you would appear to freeze in time, slowly turn red, and disappear. While from your perspective, you can watch the rest of the universe in fast forward, kind of like seeing into the future. Right now, we don't know what happens next, but we think it could be one of two things. 1. You die a quick death. A black hole curves space so much that once you cross the event horizon, there is only one possible direction. You can take this literally. Inside the event horizon, you can only go in one direction. It's like being in a really tight alley that closes behind you after each step. The mass of a black hole is so concentrated, at some point even tiny distances of a few centimeters would mean that gravity acts with millions of times more force on different parts of your body. Your cells get torn apart as your body stretches more and more until you're a hot stream of plasma, one atom wide. 2. You die a very quick death. Very soon after you cross the event horizon, you would hit a firewall and be terminated in an instant. Neither of these options are particularly pleasant. How soon you would die depends on the mass of the black hole. A smaller black hole would kill you before you even entered its event horizon, while you probably could travel inside a supermassive black hole for quite a while. As a rule of thumb, the further away from the singularity you are, the longer you live. Black holes come in different sizes. There are stellar mass black holes with a few times the mass of the Sun and the diameter of an asteroid. And then there are these supermassive black holes which are found at the heart of every galaxy and have been feeding for billions of years. Currently, the largest supermassive black hole known is S50014+81, 40 billion times the mass of our Sun. It is 236.7 billion kilometers in diameter, which is 47 times the distance from the Sun to Pluto. As powerful as black holes are, they will eventually evaporate through a process called Hawking radiation. To understand how this works, we have to look at empty space. Empty space is not really empty, but filled with virtual particles popping into existence and annihilating each other again. When this happens right on the edge of a black hole, one of the virtual particles will be drawn into the black hole and the other will escape and become a real particle. So the black hole is losing energy. This happens incredibly slowly at first and gets faster as the black hole becomes smaller. When it arrives at the mass of a large asteroid, it's radiating at room temperature. When it has the mass of a mountain, it radiates with about the heat of our Sun, and in the last second of its life, the black hole radiates away with the energy of billions of nuclear bombs in a huge explosion. But this process is incredibly slow. The biggest black holes we know might take up to a googol years to evaporate. This is so long that when the last black hole radiates away, nobody will be around to witness it. The universe will have become uninhabitable long before then. This is not the end of our story. There are loads more interesting ideas about black holes. We'll explore them in part 2. What if our universe comes with a self-destruct button to eliminate itself so cleanly and efficiently that every single physical thing would just stop existing and life would be impossible forever? The ultimate ecological catastrophe: vacuum decay. To explain how our universe could destroy itself, we need to understand two principles. 1. Energy levels. A core idea in physics is that everything has an energy level. The higher the level, the more energy is in the system. Wood, for example, has a high level. It can be burned, a process that releases the chemical energy stored in its molecular bonds and turns it into heat. The ash left over is at a lower energy level than the wood before. 2. Stability. Everything in our universe tries to move towards its ground state, in which it's completely stable and has as little energy as possible. For example, a ball on a hill is unstable and has a lot of potential energy. When disturbed, it will roll down into the valley and lose its potential energy in the process. The ball is now in its ground state and stable. It will remain like that. Everything in our universe follows these two principles. If something has a lot of energy, it's unstable and wants to get rid of it to become stable and reach its ground state. This is true for every system, even in the weird world of quantum mechanics. If our current understanding of physics is correct, then the universe gets its properties from quantum fields. We explained them in detail in another video. For this video, imagine them as the rules of the universe. They tell particles how to behave and interact. Like everything in the universe, they want to be in the lowest energy level possible, which is called a vacuum state. This has nothing to do with vacuum in space. It's just called this way because scientists are bad at naming things. We think all the fields reached their vacuum state, except maybe one. It's possible that the Higgs field is not stable, but metastable, which is a fancy way of saying that it pretends to be stable, but really is not. It would be a false vacuum. The Higgs field is responsible for giving particles their mass, which rules how almost everything in the universe interacts. What would happen if the Higgs field is in a false vacuum? Think of our ball in the valley. The ball is the Higgs field. The valley might not be the lowest energy state for the Higgs field. There might be an even deeper valley that it wants to get to. This would mean that the Higgs field has a lot of potential energy waiting to be released. The Higgs field could be like a piece of wood, but drenched in gasoline, waiting to set the universe on fire. A random spark, like quantum tunneling, could release the potential energy of the Higgs field. This could happen at any time and without warning. If at any point in space this so-called vacuum decay starts, there is no turning back. As the Higgs field crashes into the lower energy state, it releases a massive amount of potential energy. This energy pushes the space around it over the barrier, which releases more potential energy. A sphere of the new stable Higgs field or true vacuum grows at the speed of light in all directions. Imagine it like setting a sea of gasoline the size of the universe on fire. The sphere is surrounded by a shell of energy that devours everything it comes into contact with. Whatever it touches is eliminated from existence. The bubble will continue to grow forever, deleting the universe on its way. There is no way to be warned since it's so fast, but there's nothing we could do anyway. Our destruction would be instant. In a fraction of a second, Earth would be gone. But it actually gets worse. If the energy level of the Higgs field changes, it changes all of physics. In the true vacuum of the sphere, the standard model will be overthrown, superseded by different physics that we don't know. How fundamental particles behave, how atoms hold together, how chemicals react. Vacuum decay won't just destroy life, it will destroy chemistry itself, making life as we know it impossible. We simply have no idea what it would be like inside. It might be a shadow of what it is now. Or not. We don't know. If vacuum decay happens, the outlook is indeed grim. If you feel slightly worried now, don't be. At this point, false vacuum is speculation based on our current understanding of particle physics, which might be wrong. It's kind of like using a ruler to measure a continent. Sure, you can do it, but you might be off by quite a bit at the end. Right now, no one can say if vacuum decay is a thing that's real or just a scary idea. But even if one or multiple spheres of death have already started expanding, the universe is so big that they might not reach us for billions of years. If they're far enough away, they might not ever be able to reach us because of the expansion of the universe. The speed of light is not that fast on the scale of the universe. So while vacuum decay is fascinatingly scary, right now there are other things we should be more afraid of. In contrast to vacuum decay, we have the power to prepare for most of them. Leaving Earth to find new homes in space is an old dream of humanity and will sooner or later be necessary for our survival. The planet that gets the most attention is Mars, a small, toxic and energy-poor planet that just about seems good enough for a colony of depressed humans huddled in underground cities. But what if we think bigger? What if we take Venus, one of the most hostile and deadly places in the solar system, and turn it into a colony? Not by building lofty cloud cities, but by creating a proper second Earth. It might be easier than you think. Venus is by far the hottest planet in the solar system with a surface temperature of 460 degrees Celsius, hot enough to melt lead. This heat is due to the most extreme greenhouse effect in the solar system. CO2 is great at trapping heat. Even a rise from 0.03% to 0.04% in Earth's atmosphere is heating up our planet right now. Venus's atmosphere is 97% CO2. Also, Venus's atmosphere is 93 times denser than Earth's. Standing on Venus's surface would feel like taking a dive about 900 meters deep into the ocean. The pressure would kill you instantly. It's a truly horrible place, so why should we even bother? First and foremost, Venus is almost as big as Earth and has 90% of its surface gravity. Surface gravity is a big problem when colonizing the solar system because it's very likely that long stays in low-gravity places will have negative health effects. Venus's size means it could be the second largest habitat in the solar system. A new home for billions of humans and trillions of animals, with oceans, lush forests, and a beautiful blue sky. A properly terraformed Venus may be the most pleasant place to live outside of Earth. While we can't exactly terraform Venus today, a slightly more ambitious future version of us could take this project on. It will take a few generations to complete and be a huge challenge like building the Great Pyramids was for our ancestors. But then, it's not like humans have never started projects that took more than a lifetime to complete. Okay, let's do it. Before anything else, we need to cool Venus down and remove the gas that makes up the extremely heavy atmosphere. As mentioned, there's a lot of it. Around 465 million billion tons. How do we do that? There are a few options. We could create giant solar collectors powering a huge array of laser beams that heat up the atmosphere so much that it's blasted into space. Although we would need thousands of times the entire power generating capacity of humanity, and it would still take thousands of years to remove the atmosphere. Another way is to sequester the atmosphere, binding the CO2 in different compounds through chemical reactions. We could mine elements like calcium or magnesium on Mercury and shoot them at Venus via mass driver systems, electric rails that make rockets unnecessary on smaller planets. The metals would combine to bind the CO2 into different carbonates basically forever. But the scale makes the whole thing impractical. We would need several 100 billion tons of material to sequester the CO2 this way. Seems like a waste of material and might take too long. An equally ridiculous idea that could actually work is to put Venus in the shade, literally, by constructing a huge mirror to blot out the sun to just freeze the atmosphere. The mirror doesn't need to be complex or massive, just a very thin foil with a little structural support. Building such a large flat surface so close to the sun will turn it effectively into a solar sail and push it out of position. So instead of one giant circular object, our mirror will consist of many different pieces. Annular slats of angled mirrors can reflect sunlight from one set of mirrors to the next. Mirrors would be angled, reflecting light from one to another until the light is redirected to the back, balancing the force on the front and holding them in position. After a few years of getting the infrastructure in place, things start slowly and then escalate. For the first few decades, the atmosphere slowly cools down but stays dense and deadly, until after some 60 years, it reaches the critical temperature of 31 degrees Celsius. Suddenly, the Great Flood begins on Venus as CO2 turns to liquid at this pressure and begins to rain down. A constant global rainstorm of unbelievable proportions lasting 30 years. The pressure and temperature suddenly begin to drop in unison. For almost a century, puddles turn into lakes and oceans. The surface temperature is now minus 56 degrees Celsius and the pressure has dropped to only 7 times the pressure on Earth. Finally, at a really unpleasant minus 81 degrees Celsius, the CO2 oceans begin to freeze and the rain turns into snow. This leaves us with a frozen Venus covered in oceans as hard as rock and gigantic CO2 glaciers. What remains of the atmosphere is mostly nitrogen at about 3 times Earth's surface pressure. If you don't mind freezing and suffocating, you can now take a stroll over Venus's surface. But the frozen CO2 remains a bit of a problem. At some point, we want to warm up the planet, but if we do, the CO2 ice will melt and fill up the atmosphere again. So we need some way to keep it from doing that. One is to simply cover it all with cheap plastic insulation and cover it up with ground-up Venus rock or water oceans. Although some planetary scientists will be very stressed out about us building a new planet containing a potential time bomb like that. A few unfortunately timed volcanoes could melt a lot of CO2 at once and ruin everything. Another obvious solution is to shoot it all out into space and collect it into a small moon for storage and future use. We can make this more efficient by using mass drivers instead of rockets, but moving all that mass will still be a pretty intense challenge that will take some time to solve. Whatever we end up doing with the atmosphere, to move forward we need water, which we could get from ice moons. Europa, a moon of Jupiter, has twice as much water as Earth's oceans. Now, catching a moon and transporting it through the solar system is not exactly easy. So instead, it might be easier to cut chunks of ice off Europa with an army of construction drones and shoot them at Venus using more of those mass drivers. Space tethers could save us a lot of effort and energy here. We made a whole video explaining how they work, but in a nutshell, they are slings that can take a payload on both ends. On Europa, they do most of the work needed to catapult our ice to Venus. The ice hits the Venus tethers, which gently drop it into the atmosphere, where it falls down as snow. In exchange, the Venus tethers get to catch CO2 ice shot up from below and accelerate it into orbit. We can remove excess nitrogen using this same method to further lower our atmospheric pressure. After a few decades or centuries, Venus would be covered by a nice, shallow, frozen ocean a few hundred meters deep. It would look extremely different from today. A few continents and countless islands have formed. This is beginning to look a bit like our planet. Now the last and most magnificent phase of terraforming begins, making the atmosphere breathable and adding life. First, we need light though, and we need to heat the planet up again. A Venus day is 2,802 hours long, more than 116 Earth days. So if we just remove our giant mirror, we would grill half of our planet. Even without the massive atmosphere, temperatures would reach unbearable levels. The simplest way to create a day-night cycle and let some energy in again is with another set of mirrors to illuminate our continents and melt our water oceans, which would let us completely control how much energy we get and where it goes. The atmosphere is now mostly made up of nitrogen and basically devoid of oxygen. So the first inhabitants will likely be trillions and trillions of cyanobacteria, which can get photosynthesizing and release oxygen. We know that they can quickly turn around the atmosphere of a planet because billions of years ago they were probably responsible for turning the toxic atmosphere of our young Earth into an atmosphere with enough oxygen for more complex animal life. But not only that, cyanobacteria can fix nitrogen from the atmosphere and turn it into nutrients that can be used by living beings. This way, they will essentially fertilize our dead ocean water and prepare it for more complex organisms. On land, our colonists need to grind down some of the former Venusian surface to make soil for nitrogen-fixing plants to grow on. Eventually, billions of trees would spread, creating large forests covering massive parts of the continents. Venus would turn green. To speed things up, CO2 would be strategically released to supply the plants and cyanobacteria. Areas already covered with plants could get extra daylight from our orbital mirrors, so the plants would be active for most of each day. Maybe we won't have to do this with the same plants and animals we know today. As genetic engineering matures and our understanding of genetics and the machinery of life expands, we might just engineer life as we need it. All in all, it would take several thousand years to make the atmosphere breathable by humans. In the meantime, you could stroll around with nothing more than regular clothes and an oxygen mask. Settlers would enjoy a vast new planet filled with resources and bathed in sunlight. They might think of new ways to use the vast amounts of carbon dioxide ice and nitrogen orbiting in space above. Industrial processes, rocket fuel, or even boosting the terraforming of another planet like tiny Mars. Venus is fully terraformed. Animals roam through vast ecosystems. Cities are being constructed. Billions of settlers and their descendants make this world their home. They will see images of the past, how Venus was once the most hostile planet around, how it took hundreds of years to freeze hell and to ship in the oceans, and another few thousand years to make it possible to breathe freely. They will barely be able to believe it. Okay, maybe it's not that easy to terraform Venus, and a lot of things must go right for this future to become reality. But it is possible, and with technology that is within the reach of a motivated and slightly more advanced humanity that wants to venture into space. The only thing that's stopping it is our imagination, and that at least is a problem that's easy to overcome. One day the last star will die, and the universe will turn dark forever. It will probably be a red dwarf, a tiny kind of star that's also one of our best bets to find alien life and might be the last home of humanity before the universe becomes uninhabitable. So what do we know about them, and why are they our last hope? At least 70% of stars in the universe are red dwarfs. They are the tiniest stars out there, with only about 7 to 50% of the mass of our Sun, not that much bigger than our planet Jupiter, which is still huge though. They are also very dim. It's impossible to see them with the naked eye. You've never seen one in the night sky. Even with all our technology, we can only clearly observe red dwarfs in our neighborhood. Approximately 20 of the 30 stars close to Earth are red dwarfs. Like all stars, red dwarfs fuse hydrogen into helium. But while more massive stars accumulate all the fused helium in their cores, red dwarfs stay convective, meaning that the helium and hydrogen constantly mix. So they use up their fuel incredibly slowly before they're extinguished. Red dwarfs burn so slowly that their average lifespan is between 1 and 10 trillion years. By comparison, the Sun will survive for another 5 billion years. Because the universe is only 13.75 billion years old, not a single red dwarf has reached later development stages. Every single one of the trillions that exist is still a baby. Speaking of babies, the smallest star in the entire universe is also a red dwarf, because small red dwarfs are right on the verge of being a star at all. Just a tiny bit less hydrogen, and they are mere brown dwarfs, failed stars that cannot sustain a fusion reaction for long. So what about aliens, or a new home for humanity? Since our Sun will die one day, we'll eventually need to look for a new home. And where there are habitable planets, there might also be aliens. The Kepler Space Observatory found that at least half of all red dwarfs host rock planets between 1/2 and 4 times the mass of our Earth. Many of them are in the habitable zone, the area around a star where water can be liquid. But since red dwarfs burn at relatively cold temperatures, a planet would need to be really close to be hospitable, probably as close as Mercury to our Sun, or even closer. Which brings with it all kinds of problems. For example, a planet this close to a star would probably be tidally locked, meaning the same side would always face it. This side would be incredibly hot, while the shadow side would be frozen, which makes it hard for life to develop. Although a planet with a big enough ocean might be able to distribute the star's energy and create some kind of stability. Or the gravitational forces of the red dwarf could squeeze the planet and heat it up so much that it might lose all its water over time. These planets could end up like Venus, a hot, burning hell. Another problem is that many red dwarfs vary in their energy output. They can be covered in star spots that can dim their emitted light by up to 40% for months, which would cause oceans on planets to freeze over. At other times, they can emit powerful solar flares, sudden outbursts of energy, incredibly powerful. These red dwarfs can double their brightness in minutes, which could strip away sizable portions of a planet's atmosphere and burn it, rendering it sterile. On the other hand, their extremely long lifespan is a big plus. A red dwarf with just moderate levels of activity could be an amazing place for a planet that hosts life. Life on Earth has existed for about 4 billion years, and we have about 1 billion years left before the Sun becomes so hot that complex life on Earth will become impossible. We will either die out or leave Earth and look for a new home. We could build a civilization for potentially trillions of years around a red dwarf with the right conditions. About 5% of the red dwarfs in the Milky Way may host habitable, roughly Earth-sized planets. That would be more than 4 billion in total. But life may not even need a planet like Earth. Candidates for life around a red dwarf may be the moons of gas giants, or so-called super-Earths, really massive rocky planets. All in all, there are an estimated 60 billion potentially habitable planets around red dwarfs, and that's in the Milky Way alone. So red dwarfs might become really important for our survival in the future. But everything has to die at some point, even red dwarfs. When in trillions of years the life of the last red dwarf in the universe is about to end, it will not be a very spectacular event. As its hydrogen runs out, it shrinks, becoming a blue dwarf, burning out completely. After its fuel is spent, it's transformed into a white dwarf, an object about as small as Earth, packed very densely and made of degenerate gases, mostly of helium-4 nuclei. Having no more source of energy, it will cool extremely slowly over trillions of years until it becomes its final form, a cold black dwarf. White and black dwarfs are so fascinating that they deserve their own video. Anyway, it's going to be a long time before the last stars in the universe vanish. It's kind of uplifting to know that if humanity succeeds in venturing into space, we have plenty of time before the universe turns out the lights. The beginning of everything, the Big Bang. The idea that the universe was suddenly born and is not infinite. Up to the middle of the 20th century, most scientists thought of the universe as infinite and ageless. Until Einstein's theory of relativity gave us a better understanding of gravity, and Edwin Hubble discovered that galaxies are moving apart from one another in a way that fits previous predictions. In 1964, by accident, cosmic background radiation was discovered, a relic of the early universe, which together with other observational evidence made the Big Bang the accepted theory in science. Since then, improved technology like the Hubble telescope has given us a pretty good picture of the Big Bang and the structure of the cosmos. Recent observations even seem to suggest that the expansion of the universe is accelerating. But how did this Big Bang work? How can something come from nothing? Let's explore what we know. We can ignore the beginning part for now. First of all, the Big Bang was not an explosion. It was all space, stretching everywhere, all at once. The universe started very, very, very small and quickly expanded to the size of a football. The universe didn't expand into anything, space was just expanding into itself. The universe cannot expand into anything because the universe has no borders. There is, by definition, no outside the universe. The universe is all there is. In this hot, dense environment, energy manifested itself in particles that existed only for the tiniest glimpses of time. From gluons, pairs of quarks were created, which destroyed one another, perhaps after giving off more gluons. These found other short-lived quarks to interact with, forming new quark pairs and gluons again. Matter and energy were not just theoretically equivalent, it was so hot they were practically the same stuff. Somewhere around this time, matter won over antimatter. Today, we're left with almost all matter and nearly no antimatter at all. Somehow, 1,000,000,001 matter particles were formed for every 1,000,000,000 particles of antimatter. Instead of one massive ultimate force in the universe, there were now several refined versions of it acting under different rules. By now, the universe has stretched to 1,000,000,000 kilometers in diameter, which leads to a decrease in temperature. The cycle of quarks being born and converted back to energy suddenly stops. From now on, we work with what we have. Quarks begin forming new particles, hadrons, like protons and neutrons. There are many, many combinations of quarks that can form all sorts of hadrons, but only very few are reasonably stable for any length of time. Please take a moment to appreciate that by now, only 1 second has passed since the beginning of everything. The universe, which has grown to 100 billion kilometers, is now cold enough to allow most of the neutrons to decay into protons and form the first atom, hydrogen. Imagine the universe at this point as an extremely hot soup, 10 billion degrees Celsius, filled with countless particles and energy. Over the next few minutes, things cooled and settled down very fast. Atoms formed out of hadrons and electrons, making for a stable and electrically neutral environment. Some call this period the Dark Age because there were no stars and the hydrogen gas didn't allow visible light to move around. But what's the meaning of visible light anyway, when there's nothing alive yet that could have eyes? When the hydrogen gas clumped together after millions of years and gravity put it under great pressure, stars and galaxies began to form. Their radiation dissolved the stable hydrogen gas into a plasma that still permeates the universe today and allows visible light to pass. Finally, there was light. Okay, but what about the part we didn't talk about? What happened right at the beginning? This part can be defined as the Big Bang. We don't know at all what happened here. At this point, our tools break down. Natural laws stop making sense. Time itself becomes wibbly-wobbly. To understand what happened here, we need a theory that unifies Einstein's relativity and quantum mechanics, something countless scientists are working on right now. But this leaves us with lots of unanswered questions. Were there universes before our own? Is this the first and only universe? What started the Big Bang, or did it just occur naturally based on laws we don't understand yet? We don't know, and maybe we never will. But what we do know is that the universe as we know it started here and gave birth to particles, galaxies, stars, the Earth, and you. Since we ourselves are made of dead stars, we are not separate from the universe. We are part of it. You could even say that we are the universe's way of experiencing itself. So let's keep on experiencing it until there are no more questions to ask. Black holes are the most powerful things in the universe, strong enough to rip whole stars into atom-sized pieces. While this is scary enough, they have an even more powerful and dark property: they might delete the universe itself. Black holes in a nutshell. A black hole appears when an extraordinary amount of matter is concentrated in a tiny space. At their center, gravity is almost infinitely strong, and whatever gets too close is ripped into its elementary particles. Not even light can escape black holes, and so we perceive them as spheres of blackness. If you were to fall into a black hole, nothing bad would happen until well after you crossed its outer border, the event horizon. You can imagine this as swimming in a river that ends in an enormous waterfall. As you float along, imperceptibly, the stream gets faster and faster, even if you can't see the waterfall yet. You could swim to safety until, without even noticing it, you cross the point of no return. No matter how fast you try to swim now, the stream will pull you towards certain death. Nothing can escape a black hole waterfall once it gets too close. This border completely separates black holes from the rest of the universe. We can't access them unless we're willing to never return. So there's no way of telling what's really going on inside black holes, but we have a few ideas about what's going on right at their very edges. Black holes radiate their mass away, like a hot pot on a stove losing its water as steam. This is called Hawking radiation. Black holes constantly lose an extremely tiny amount of their mass, a process that's unbelievably slow. It will take a black hole with the mass of our Sun 10,000 billion years to lose 0.0000001% of its mass. This is happening constantly and unstoppably, and as it goes on, it speeds up more and more. In the far, far future, when the last star in the universe has been dead for trillions of years, black holes will become tinier and tinier until they evaporate and disappear, leaving behind just a bit of radiation. But this is a problem, because in the process of disappearing, black holes might delete something fundamental: information. 2. What is information? Information is nothing tangible. It's typically understood as a property of the arrangement of particles. What does this mean? Imagine a bunch of carbon atoms. Arrange them in a certain way and you get coal. Arrange them in a different way and you get a diamond. The atoms are the same. What changes is the information. If we make this more complex and add in a few more atoms, we get a banana. Change the arrangement of the atoms and we get a squirrel. The basic building blocks of everything in the universe are the same and don't care if they're part of a bird or a rock or a cup of coffee. Without information, everything in the universe would be the same. According to the theory of quantum mechanics, information is indestructible. It might change shape, but it can never be lost. For example, if you burn a piece of paper, you get ash. That ash will never become paper again. But if you were able to carefully collect every single carbon atom in the ash and measured the exact properties of the smoke and heat radiating from the fire, you could, in theory, reconstruct the paper. The information of the paper is still in the universe. It's not lost, it's just hard to read. If you could somehow measure every single atom and particle and wave of radiation in the universe, you could see and track every bit of information there is. Hypothetically, you could see the entire history of the universe right back to the Big Bang. And here, black holes trip us up. Information tells us how things are different from each other and what used to be what. Black holes do the opposite. They take different things and make them the same. They destroy information. This creates the information paradox, and this is a serious problem. The information paradox. It's fundamental for all our laws of physics that information can never be lost. Existing, not existing, without information, everything is relative. When it comes to our understanding of reality, we need absolutes. How could we solve this paradox? There are a few possibilities. 1. Information is lost, irretrievably and forever. This means we have to nix all our laws of physics, throwing out a lot of stuff that's worked very well so far and start from scratch. What those new laws of physics would look like, or what that means for us, nobody knows. This is a little frightening, but also kind of exciting. 2. Information is hidden. Maybe a little part of the black hole splits off and forms a baby universe. The information would be transferred into this new, weird place where we could never observe or interact with it, but technically it would not be lost. It's like having a broken hard drive with all your family photos that you could never access. Sure, it's nice that they've not been deleted, but also not very helpful. Or maybe black holes don't disappear completely after the end of their life cycles, but a little piece is left, an information diamond. Like a clown car filled with an infinite amount of information clowns. But there's a third option. Information is safe after all, not lost or hidden. Perhaps we've just been looking at this whole thing the wrong way. We know that black holes trap information and might delete it later, but we never thought about what they do with it in the meantime. Where do black holes store their information? Cosmic housekeeping. Let's create a black hole with dirty laundry. First, we fill up a room with laundry baskets. The more laundry you want to store, the more baskets you put in the room. But at some point, every single basket is full and the room is completely stacked. Not a single extra sock fits in. The room is at maximum capacity. But if we still squeeze the sock in with a lot of energy and violence, the room collapses in on itself and forms a black hole. But the capacity of the room itself has not changed. Fitting in more stuff or information is still impossible. So what happens if we throw more laundry into it? The room itself gets a little bit bigger to make space for the new information. It turns out a black hole grows its surface by a tiny pixel for each bit of information we throw into it. In a nutshell, more information means more surface area. The information gets painted on the surface, similar to what happens when we throw a stone into a pond. After the stone sinks to the bottom, we can't see it anymore, but we can tell that something went in from the ripples on the surface of the pond. Even the smallest black hole can store more information on its surface than all the data ever produced in human history. They do this by storing information in a type of pixel that is unbelievably tiny. Black holes are the ultimate hard drive. This is a bit like taking a paperback and turning it into an ebook. Two things that look completely different, but their content is the same. It's just encoded and memorized in another way. Black holes swallowing stars and planets is a bit like transferring a whole library onto an e-reader. This solution is called the holographic principle. But if it's correct, then everything we thought we knew about the universe is wrong. The universe is a hologram. If information is actually stored on the boundary of a black hole, the Hawking radiation has a chance of learning about the information encoded there and can carry it away. So, information is not lost when black holes fade away, and we do not need to redo physics. The information paradox is resolved. But we still have to change our understanding of reality in a fundamental way. If everything that falls into the black hole is stored on its event horizon, that basically means that three-dimensional stuff is encoded on a flat surface. We have a name for this, a hologram. A hologram is like a 3D photo, a flat piece of plastic that encodes a three-dimensional image. A black hole is like a hologram because everything inside it is encoded on its event horizon. A person inside a black hole would experience their usual three-dimensional life. But for us on the outside, they are flattened images on the surface of the black hole. The consequence of this is counterintuitive, but stay with us for a moment. Black holes are very extreme objects, but they're still bound to the same rules as everything else. So if this crazy duality between 2D and 3D works for black holes, then it might work for the whole universe and you in it. Since a person inside a black hole would not realize that they're encoded on a flat surface, we might share the same fate. You really might be stretched over a flat screen at the end of the universe. The science behind this is complicated and really weird, with toy universes to play with, string theory, and a lot of maths. We'll talk about this more in another video. Regardless of what the true nature of the universe really is, we just know that it's strange and complicated, and we have to do a lot more physics to understand it. But black holes might be key to understanding the nature of reality itself. How big is the moon? In the night sky, the moon seems rather small, but in reality, it really isn't. Central Europe would easily fit under it. The surface area of the moon is huge. To give you some perspective, it's as big as the whole European continent, China, the USA, Brazil, and South Africa together. Weight-wise, the moon is only about 1/81th of the mass of Earth. But how big is it in relation to Earth? Quite big, actually. Our moon is the biggest in the solar system in relation to its planet, and it's the 5th largest moon in the solar system, quite a bit bigger than the dwarf planet Pluto. Now, if the moon is really that huge, how far away is it from us to seem this small in the night sky? 370 kilometers, as far as the ISS maybe? No, at that distance, gravitational forces would rip the moon apart. At 36,000 kilometers, it would be as far away as our most distant satellites. Let's adjust the distance to reality. Pretty far away, right? A 747 would need 28 straight days to fly to the moon, and even with our current technology, we'd need 2 full days. And in a car, a lot of time. So, how big is the moon? Well, it kind of depends how you define big. But seriously though, it's pretty big. One day the universe will die. But why and how? And will the universe be dead forever? And how do we know that? First of all, the universe is expanding. And not only that, the rate of its expansion is accelerating. The reason? Dark energy. Dark energy is a strange phenomenon that scientists believe permeates the universe. Until 1998, we thought that the universe must work a bit like a ball that you throw into the sky. The ball moves up, but at some point it has to come down again. But the expansion of the universe is actually speeding up. That's like throwing a ball up and watching it fly away faster and faster and faster. Where is this acceleration coming from? Well, we don't know, but we call it dark energy. Einstein thought of it first and then decided it was stupid. Now, astrophysicists have decided it is plausible. Trouble is, this is all very theoretical, and we don't actually know what the properties of dark energy are. But there are various theories, and they lead us to 3 scenarios for the end of the universe. 1. The Big Rip. Since its birth, the universe has been expanding. For unknown reasons, new space is created everywhere equally. The space between galaxies expands, so they move apart. The space inside galaxies also expands, but here gravity is strong enough to keep them together. In the Big Rip scenario, the expansion accelerates up to a point where space expands so fast that gravity can't compensate for this effect anymore. The result is a Big Rip. At first, only large structures like galaxies are torn apart since space between the single objects expands very fast. Next, big bodies like black holes, stars, and planets die. Their gravity isn't strong enough to keep them together, so they dissolve into their components. In the end, space would expand faster than the speed of light. Atoms would now be affected, and they would just disband. Once space is expanding faster than light, no particle in the universe can interact with any other particle anymore. the universe would dissolve into countless lonely particles that won't be able to touch anything else in a strange, timeless universe. And you thought you felt lonely. 2. Heat death, or a big freeze. In a nutshell, the difference between the Big Rip and heat death is that in a heat death scenario, matter stays intact and is converted over an incredibly long but finite period of time into radiation while the universe expands forever. But how does this work? Let's talk about entropy. Every system tends towards the state of highest entropy, like when we have a latte macchiato. Initially, it has different regions, but over time they will cool down and disintegrate until it's uniform. And this also applies to the universe. So while the universe gets bigger and bigger, matter slowly decays and spreads out. At some point, after lots of generations of stars, all the gas clouds necessary to form stars will be exhausted, so the universe will turn dark. The remaining suns will die. Black holes will slowly degenerate and evaporate over trillions of years due to what's known as Hawking radiation. When this process is complete, only a dilute gas of photons and light particles remains until even this decays. All activity in the universe ceases at this point. Entropy is at its maximum, and the universe is dead forever. Unless, theoretically, it might be possible that after an incredibly long amount of time, there might be a spontaneous entropy decrease as a result of something called quantum tunneling, leading to a new Big Bang. 3. Big Crunch and Big Bounce. This is the most uplifting scenario. If there is less dark energy than we think, or it decreases over time, gravity will be the dominating force in the universe one day. In a few trillion years, the rate of expansion of the universe will slow down and stop. After that, it reverses. Galaxies will race at each other, merging as the universe becomes smaller and smaller. Since a smaller universe also means a hotter universe, temperatures rise everywhere all at once. 100,000 years before the Big Crunch, background radiation would be hotter than the surfaces of most stars, which means that they would be cooked from the outside. Minutes before the Big Crunch happens, atom cores are ripped apart before supermassive black holes devour everything. Finally, all black holes would merge into a supermassive mega black hole that contains the entire mass of the universe, and in the last moment before the Big Crunch, it would devour the universe, including itself. The Big Bounce theory states that this has happened a lot of times and that the universe goes through an infinite cycle of expansion and contraction. Well, wouldn't that be nice? So what will actually happen to the universe in the end? At the moment, heat death seems the most likely, but we at Kurzgesagt hope that this dead forever stuff is wrong and the universe will start over and over again. We don't know for sure either way, so let's just assume the most uplifting theory is true. Is the universe infinite? Does it have an edge? And if so, what would you see if you went there? Today, we know that the universe had a beginning 14 billion years ago and that it's been expanding ever since. But something that's expanding should also have an edge, right? Well, it sort of does. Information can't travel faster than light. That means that we can only see parts of the universe whose light has had time to reach us in the last 14 billion years. When we look outwards, what we see is a sphere centered on us, the observable universe. But it gets a tad more complicated. Because the universe has been expanding, we know that the most faraway things whose light we can see are actually 45 billion light-years from us right now. So the observable universe is a sphere with a radius of 45 billion light-years. It contains around 200 billion galaxies, each with hundreds of billions of stars. So for us, there is an edge. We're looking at the past until there is just no past left. This edge is really more like an edge in time and, in a sense, meaningless. The real universe is for sure bigger than what we can see. But how much? There are two options. Either the universe is really big but finite, or it's truly infinite. A finite universe means that if you want to fill it with ice cream, you can do it. You need a lot of ice cream, but it is a finite amount. But that leads to a weird problem. Such a universe should have an edge, a cosmic wall where space ends. And if there's an edge, there should be something outside that edge. But the universe by definition is all there is, so how could there be stuff outside all there is? Does the idea of something outside of everything even make sense? Except, of course, there is a physics hack. You can have a universe that has no border, but that still could be filled with a finite amount of ice cream. What if the universe is truly finite? Imagine an orange and a really tiny ant. The ant can only see a small piece of the skin, just as you can only see a small chunk of the universe. But if the ant starts walking, it will eventually walk around the whole orange and be back to its starting point. So the skin of an orange is not infinite, but it doesn't have a border. The universe is not like the skin of an orange, but it could be very similar. Instead of a sphere, it could be a hypersphere, where 3D space is curled on itself. Which is impossible for your brain to visualize, unfortunately. But the point is, no borders, no outside of the hypersphere. From our human ant perspective, our whole 3D space is like the peel of the orange. If you were aboard a spaceship flying in a straight line, you would eventually come back to Earth. How does any of this make sense? The actual physics is hard, so we have to simplify and lie a bit here. But in a nutshell, it all boils down to gravity. The way it works is that mass creates gravity by bending space-time. This bending is the strongest where the mass is, but sort of stretches on forever, like a very mild tension in the fabric of space-time itself. This could bend the whole universe in a way where it bends back on itself, which then makes the hypersphere. If you find this confusing, we're with you. If the universe happens to be a hypersphere, how could we find out how big it is? On Earth, we can see things disappear below the horizon, and that helps us calculate how big the Earth is. Scientists tried to find some sort of universe horizon that would reveal the scale of the cosmic sphere, but didn't see anything. Which means that if the universe is a hypersphere, it needs to be so big that from our perspective, it looks like we're living on a flat surface. For this to make sense, a hyperspherical universe should be at least 1,000 times bigger than our observable part. It could be 1 trillion times bigger for all we know, but not smaller than that. Some scientists thought all of this is way too straightforward and came up with a wilder option. The universe could be like the frosting of a donut. A hyperdonut, also impossible to visualize for your brain. This too means that if you travel in a straight line, you'd get back to where you started, but with fun complications. In a hyperdonut universe, there's not the same amount of stuff in every direction. If 2 spaceships fly in different directions, one could get back to the start way earlier. This also means that light from faraway galaxies would do fun and confusing stuff in a sort of cosmic Hall of Mirrors effect. We could see faraway things in 2 places, but not just that, we would see it in different moments in time, because its light would have taken much longer to travel in one direction than the other. You could see a star being born in front of you and see that same star die on the opposite side of the sky. How big would such a hyperdonut universe be? Well, because of its strange geometry, actually this is kind of the smallest possible universe, potentially just a few times bigger than the observable universe. But it could also be way, way bigger. We don't know. Okay, so much for finite universes. But what if it's truly infinite and space goes on forever? What would that be like? What if the universe is truly infinite? Actually, the cosmological model used by most scientists describes an infinite universe. We mostly use it to calculate what happens inside our observable chunk, but if taken literally, it predicts an infinite universe. An infinite universe goes on, well, forever, with no border anywhere, also impossible to visualize. Wherever you look, you'll find more and more stuff in every possible direction. This kind of breaks our brain a bit for a few reasons. First of all, if the universe is infinite, is it also eternal and has been there forever? Was there a time when there was nothing everywhere, and then there was something everywhere? Well, we don't know, but we have a lot of evidence for the Big Bang, so it really seems like the universe started at some point in the past. But wait, since the Big Bang, the universe has been expanding. How can an infinite thing that's everywhere become even bigger? Cosmic expansion just means that the distance between galaxies is growing with time. even an infinite space can become bigger. Welcome to the paradoxes of infinity. Infinity gets much weirder though. As you travel with your spaceship in a straight line, you find new galaxies, stars and planets, new wonders, new weird stuff, probably new aliens and new life forms stranger than you could ever imagine. But after a long time, you might find the most special thing in the universe, yourself. An exact copy of you watching this video right now. How can that be? Well, everything in existence is made of a finite amount of different particles. And a finite number of different particles can only be combined in a finite number of ways. That number may be so large that it feels like infinity to our brains, but it's not really. If you have finite options to build things, but infinite space that is full of things in all directions forever, then it makes sense that by pure chance, there will likely be repetition. Although, just because something is possible, doesn't mean it will actually happen. Maybe the universe goes on forever, but only the boring stuff repeats itself endlessly. Maybe there is really only one you. But if the laws of physics are the same everywhere, then far, far away, gas could have given birth to stars and planets where primitive genetic information could emerge from chemistry, which might have ended up in cells and animals that evolved in really unlikely ways, and eventually apes that learn how to create online videos. It happened at least once, so the chance is not zero. Even if the chance of there being an exact copy of you watching this video right now is almost zero is still a huge number in an infinite universe. Unfortunately, you'll never meet, because almost zero still means the chance is incredibly small. Earth, as it exists right now, is so unlikely you'd have to travel incredibly far to find a second identical Earth. Some 10 to the 10 to the 29, a 1 followed by 100 octillion zeros, times the size of the observable universe. So far that it kind of means forever far away. Still, in a truly infinite universe, every combination of particles could reasonably not just occur only once, but an infinite number of times. It's time to stop now. While these scenarios are possible on paper, we've entered science philosophy here. Currently, none of these ideas are testable or provable. If the universe is infinite, we will never know. The reality is, for us, the universe is finite and has an edge. And we can see the edge in time. Everything we can interact with is within the observable universe, and most likely, this will stay true forever. Even if this finite universe feels small to you, it's more than big enough to fulfill all the dreams that we and our descendants can ever come up with. Infinitely enough for all of us. Human history is told by the energy we use. At first, we had to use our muscles, then we learned to control fire. We industrialized the world using coal and oil and entered the atomic age when we learned how to split a nucleus. At each step, we increased our energy harvest to a scale never seen before and advanced as a species. Currently, we're slowly transitioning to renewables, and if we're lucky, fusion energy will become viable in the future. As humanity progresses further, if we don't destroy ourselves or our habitat, we will likely gain complete control of our planet's resources. At that stage, we'll probably begin to look outwards for new places to expand into. But space is hard, and establishing a serious human presence in the solar system will require ungodly amounts of energy. Luckily, we know where to find it. The Sun, the ultimate source of energy. A furnace 100 quintillion times more powerful than our most efficient nuclear reactor. It shines with the energy of 1 trillion nuclear bombs per second. So how do we get this energy? Not some of it, all of it. If we want to collect the most energy physically possible, we'll have to build the largest, most ambitious structure in the universe, the Dyson sphere, a megastructure that encompasses a whole star to capture its power output. For an intelligent species, building a Dyson sphere is a technological leap on a par with the discovery of fire for our ancestors. The transition from a planetary species to an interstellar species. It would usher in an age of exploration and expansion on a scale we can barely imagine. So, what would it look like? A solid shell enveloping the Sun is probably not the way to go. A large rigid body like that would be vulnerable to impacts, possibly shattering. It would be liable to drift and could crash straight into the Sun. A more viable design for a Dyson sphere might be a Dyson swarm, an enormous set of orbiting panels that collect the sun's power and beam it elsewhere. Such a swarm would give humanity basically unlimited energy. But building it won't be easy. The sun is very big, so we need a lot of satellites. If each satellite is a square kilometer, we'd need around 30 quadrillion to surround the sun. Even if they're built as lightly as possible, we need about 100 quintillion tons of material. And then we need the energy to actually put the parts together and deliver them to their positions around the sun. On top of all that, we need to have a permanent infrastructure set up in space to start building. Let's assume for the purposes of this video that our descendants will take care of that and want to create the megastructure. We can sort the challenges into three main categories: materials, design, and energy. To get the vast amounts of raw materials required for our Dyson swarm, we'll have to largely disassemble a whole planet. Of the planets available, Mercury is the best candidate. It's the closest to the Sun and very metal-rich. Close to the Sun also means less moving stuff around, and Mercury has no atmosphere and only about a third of the surface gravity of Earth, making it comparatively easy to launch material into space. Next, we should consider the design of our swarm. Simpler is better. Conventional solar panels are far too intricate and short-lived. Our satellites need to operate without repairs or intervention for astronomically long times, and they need to be cheap to produce. They're most likely going to be enormous mirrors, which refocus sunlight to central collecting stations like in concentrated solar power on Earth. To build and launch them efficiently, they must be incredibly light, made of little more than polished metal foil bound to some supports. And last, we need the energy to build and launch the swarm itself. Taking apart a planet and launching things into space requires an enormous amount of energy. For example, if we used all the fossil fuels and uranium on Earth and we were perfectly efficient, we could only launch as much mass as Mount Everest into space. A rather meager accomplishment compared to planetary disassembly. To get the energy needed to build a Dyson sphere, it's almost as if you're going to need the power output of a Dyson sphere. But that's okay. There's plenty of sunlight to be had on Mercury, so let's get to work. Humans are expensive to keep alive and are very sensitive to the environment, so we'd want to automate as much as possible. Ideally, we'd have a small crew of controllers who oversee an army of autonomous machines doing the actual work. There are four major pieces of technology required: solar collectors, miners, refiners, and launch equipment. The solar collectors are going to give us the energy we need to disassemble the planet. To start, maybe we deploy something like 1 square kilometer of them, either as mirrors or as traditional solar panels. They'll provide the energy to run our miners, which strip mine the surface of the planet, and our refiners, which extract valuable elements and fabricate them into our swarm satellites. To get them into space, we need a creative and efficient solution. Rockets are too expensive and difficult to deorbit and reuse. Instead, we'll want to use a sort of railgun, a long electromagnetic track which launches our satellites at high speeds. Our swarm satellites would be packed tight for launch, unfurling like an enormous origami once in orbit. From this point, we can take advantage of exponential growth, using the energy of the existing parts of the swarm to build more infrastructure on Mercury and launch new panels faster and faster. Each panel provides the energy to build another. Those two work together to build the next two. 4 become 8, 8 becomes 16, and so on. Within just about 60 doubling times, the Sun would be completely surrounded by solar panels. And this can happen quickly. If a square kilometer of solar collectors takes a month to build, we could be done in a decade, if only our infrastructure on the planet's surface can keep up with the quickly growing budget of energy. Even collecting 1% of the Sun's energy is an unbelievable change in our species' energy budget. We could create the infrastructure to beam basically unlimited amounts of energy around the solar system for all sorts of projects. Colonies on other worlds, terraforming planets, constructing more megastructures, or even traveling to other stars. It could be the start of an interstellar civilization. Based on physics alone, this is not just possible, but easy. It's such a simple process and such a necessary step for any species to expand beyond their home planet that many astronomers think there are probably Dyson spheres already out there in the Milky Way. We haven't spotted any yet, but they could be there. It's far from certain that humanity will ever get to this point. Our attention is too often focused on short-term political gains and conflicts that will not matter in the long run. But if we survive the challenges we've set ourselves, we could potentially become the first species in the universe to create a structure with the scope of a star. If we do it, the only limitation left will be our own imagination. You might be inside a black hole that's inside a black hole that's inside a black hole. Everything in existence could be black holes all the way down. It turns out black holes are much weirder than you think, and they break the universe much more than is usually explained, destroying time and space. And they may actually create infinite universes in the process. But before we can get to that, let's first build a black hole out of air. Everything can become a black hole if you squeeze it to a critical limit. You'd need to squeeze Earth down to the size of a coin for it to turn into a black hole. The Sun needs to be squeezed down to the size of a small city to become a black hole. And if a lot of mass is concentrated in a really tiny space, you get something super dense. This is usually how black holes are explained. Stuff becomes super dense and collapses into a black hole. But actually, you don't need any ultra-dense stuff to make them. We're ignoring some maths here, but all you really need to know is one thing. The larger black holes get, the less dense they are. So, really large black holes are kind of thin. A sun mass black hole is only about 6 kilometers wide and has a density of about 1 Himalayan range per cubic meter. The supermassive black hole at the center of the Milky Way has a mass of 4 million suns, a diameter of 24 billion kilometers, and a density of 6 blue whales per cubic meter. The ultramassive black hole IRAS 2100-4156 has a mass of 3.8 billion suns and is as wide as the solar system. But because it's so large, it is only as dense as air. This means, at least in theory, that if you take a gigantic balloon and fill it with undecillions of tons of air, the moment it gets to the size of a solar system, an event horizon suddenly forms and it turns into a supermassive black hole, without violence or squeezing. So now, let's think big. What do we need to make a black hole the size of the universe? A universe-sized black hole. The chunk of the universe that we can see from Earth is a sphere with a radius of 45 billion light-years, filled with hundreds of billions of galaxies, lots of gas, and a bunch of other things. If you add them up, it has the mass of about 1 million billion suns. Which sounds a lot, but on average, the universe is not very dense. If we break up all the galaxies, stars, gas, and energy and spread them equally inside the volume of the universe, we get an average density of about 5 hydrogen atoms per cubic meter. You can imagine this as the sort of ultra-thin cosmic air that makes up the universe. What would happen if we take a balloon as big as the observable universe and fill it with cosmic air? Well, it turns out that all the mass in the observable universe is more than enough to create a black hole. Actually, it's enough to make a black hole 10 times larger than the observable universe. But that can only mean one thing. We should be living deep inside a truly gargantuan, cosmic-sized black hole. There's one catch though. We know that our universe is expanding, and an expanding universe is not what you'd expect to see if you were inside a black hole. So our universe can't be a black hole, at least not in the naive way we've just described. Except there's a wild and mind-bending trick the universe could play on us. To find out how, let's jump into a black hole and die. A whole universe born inside a black hole. We usually imagine black holes as spheres with a singularity at their center, a point where all their mass is concentrated so much that our maths breaks down. But this is a lie. They are so much weirder. From the outside, a black hole looks like a normal black sphere, but the inside is where things stop making sense. Black holes warp the universe so much that at the event horizon, space and time switch their roles. Inside a normal sphere, space is finite, but time goes on forever. But inside a black hole, it's the other way around. Space goes on forever, but time is finite. So once inside, you see an infinite universe with no center. The geometry is too complicated, so we're simplifying. But basically, you could walk forever in one direction, or walk in another direction and arrive at the same place again. But not only that, inside a black hole time is finite and it's now running out. So after a while you start to notice that space itself is slowly changing. In one direction space is being stretched, while in all other directions space is shrinking. The whole universe is being squeezed, kind of turning into a collapsing spaghetti. Sooner or later the whole black hole universe collapses into itself. All of space, every single part of it, is turning into a singularity. So the singularity of a black hole is not at its center or in any direction at all. It's in the future of whatever falls inside. We made a whole video about this if you want to learn more. So the singularity is not a place where you can go, it's an event in time that happens. Once it happens, you and everything else that fell inside the black hole will be mercilessly crushed into an infinitely small region with infinite gravity and infinite energy. Time, space, none of it matters anymore. Both kind of stop existing in ways that we would recognize. And then, is this the end? Well, maybe not. This collapse of the black hole universe into a singularity looks like one of the scenarios for the end of our universe, the Big Crunch, where long after the Big Bang the whole universe collapses into a singularity again. But if there's a big crunch, there might be a big bounce, like a rubber ball that you've squeezed too much and that suddenly rebounds. Space might expand again. So a new universe could be born inside a black hole. The funny thing about this scenario is that nothing has changed in the slightest outside the black hole. Watching from the outside, it's still a black sphere of nothingness, and yet on the inside, a new universe has been born. So maybe our universe was born like this, and we are all actually inside a black hole. But if our universe can also create black holes, they might give birth to new universes. Is our black hole universe also just part of a universe further up that's also a black hole inside another universe? Is there an end to it? Is there one original universe? Is the cosmos black holes inside black holes inside black holes? Infinite black hole universes. If the universe creates black holes that create universes, that then create new black holes that create new universes, this cosmic self-reproduction would be subject to natural selection. A Big Bang is a chaotic and messy event, so it's possible that the new daughter universes would not always be fully identical to their mums. Sometimes physics may be slightly different, with some fundamental values higher or lower, and so some universes might be able to create loads of stars, planets, and black holes. Others might not, maybe creating a uniform cosmic soup where no stars, planets, and black holes form. But if all universes are born inside black holes, in the long run all universe lines that don't create loads of black holes would die out. The universes with the conditions for loads of black holes would become the most common and spawn the most daughter universes. Survival of the fittest, but with universes instead of organisms. Our observable universe alone has created at least 10 to the power of 17 black holes so far. So maybe our universe has the physics and laws it has because it was born after a long process of cosmological selection that favored the production of tons of black holes. And that would have a lovely side effect. If universes are optimized to create as many new black hole universes as possible, they're optimized to create loads of galaxies and stars. And thereby also, by accident, the conditions for life to emerge. So universes that are the best at creating new universes are also the best at creating life. If this scenario is true, who knows how many bazillions of black hole universes might be out there, all with stars and planets potentially home to others like us. So, is our universe like this? The truth is we don't know. While these ideas are based on real science and work on paper, they're speculative and not testable. Also, cyclic universes don't actually explain why the universe exists in the first place or why it is the way it is. Instead of providing answers, these are really just new questions in disguise, so keep that in mind before getting too excited. But isn't it just wonderful and heartwarming that we're living in a universe where ideas as big as this one are even thinkable? There might be so much life. And if new universes are created constantly, maybe life will go on forever. Humans can survive in this universe as long as we have an energy source. Unfortunately, the universe will die. It will happen slowly, over many billions of years, but it will happen. On a universal timescale, stars like our Sun will be gone in no time. Luckily, there are places that will exist practically forever from a human perspective. The corpses of dead stars. White dwarfs. They could be humanity's last home right before the death of the universe. What are these strange things, and what happens when they finally die? How long stars live varies drastically, depending on how massive they are. For example, really massive stars burn hot and fast, dying violently in supernova a few million years after birth. But they're the exception. 97% of all stars will end their existence as white dwarfs. There are two ways this can happen. Small stars, so-called red dwarfs, burn out over trillions of years until they eventually quietly turn into white dwarfs. Medium-sized stars like our Sun are more interesting. Imagine the Sun as a huge pressure cooker that fuses hydrogen into helium in its core through its gravity. The fusion of elements releases extreme amounts of energy that pushes outwards and stabilizes the star, keeping it in a delicate balance. When the Sun is old, the hydrogen in the core is exhausted, and the Sun will begin to burn helium into heavier elements. While doing so, it will shed its outer layers. When this process is over, more than half of the Sun's mass will be lost into space as a spectacular planetary nebula millions of kilometers across. What remains will be its former core. A white dwarf is born, a star corpse. While its former self was about 100 times its diameter, now it's only about as big as Earth, but still with about half of its former mass. This means it's extremely dense. A teaspoon of white dwarf is about as massive as a car. Its surface gravity is over 100,000 times higher than Earth's. If you tried to land on it, you'd immediately be compressed into a steaming puddle. Life around a white dwarf is very unlikely, but possible. Most of them that exist now were former stars that, well, died, which probably ruined any planets they once had. But that's not all. Since they are so small, a planet would need to orbit them about 75 times closer than Earth is to the Sun to have liquid water. This proximity has up and downsides. For one, it would tidally lock the planet, giving it a permanent day and permanent night. At the edges of these day and night zones, life could be possible. But white dwarfs have a very stable energy output, so they might actually be safer to live around than many red dwarfs. This is still speculation at this point, but if we could find a white dwarf with the right conditions to settle around, we could have a home for many billions of years. But why do they shine so much longer than other star types? White dwarfs are very, very hot, up to 40 times hotter than our Sun, ranking among the hottest objects in the universe. But they are not incredibly active. All the heat inside of them is trapped and has nowhere to go. Only on its outer layer can it escape into space. But space is mostly empty, so heat can't be transferred by conduction. The only way energy can escape is by radiation. This is so inefficient that white dwarfs will take trillions of years to cool down, which may make them humanity's last refuge. They might be the last sources of light and energy in a dying universe. According to some estimates, white dwarfs might shine as long as 100 billion years, 10 billion times longer than the universe has existed. So far into the future that no regular stars will shine anymore. Galaxies will have evaporated. And only then will the first white dwarf turn into the first black dwarf. When this happens, the last hope for life will die off. Black dwarfs will be inactive spheres with no energy left to give. Still massive enough to kill you if you get too close. So cold that they'll be near the coldest possible temperature in the universe. So dark that they are practically invisible. the universe will enter its last stage, heat death, which will leave the universe unrecognizable. An absolutely dark and cold graveyard with black holes and black dwarfs scattered over trillions of light years. We don't know for sure what will happen with black dwarfs in the end. If the proton, one of the fundamental parts of atoms, has a limited lifespan, black dwarfs will slowly evaporate over many trillions of years. If the proton does not decay, black dwarfs will probably turn into spheres of pure iron via quantum tunneling over a time span so obscenely gigantic that calling it forever is okay. These iron spheres will then travel completely alone through a dark universe. Nothing new will happen anymore. Forever. While this may sound kind of dark, this is so far away that for our purposes today, it might as well not happen at all. It doesn't matter what happens in a billion trillion years. Right now, we happen to exist at an excellent time, able to be in awe about a universe filled with endless stars and light and planets, and enough time to visit them one day. The night sky seems peaceful and orderly. But in reality, stars are careening through the galaxy at speeds of hundreds of thousands of kilometers per hour, not bound by static formations, but changing neighborhoods constantly. Fortunately, space is big, and so the stars of the Milky Way are very unlikely to hit us. Unfortunately, they don't have to hit anything to make us have a really bad time on Earth. And there are already stars starting to get very close. To understand how dangerous stars are to us, we need to talk about gravity. Gravity attracts every piece of matter to every other piece of matter in the universe. You are attracted by an atom a million light years away and vice versa. Luckily, this force gets weaker over distance, and it also depends on how massive something is. So things that are close and are very massive are more attractive, winning the cosmic tug-of-war. This way, massive things define how smaller things behave around them. The Sun makes up 99.75% of all the mass in the solar system, and so it shapes the behavior and orbits of everything else in it. Billions of years ago, after the Sun was born, the solar system was a chaotic and dangerous place as the planets were formed from countless little pieces that collided constantly. But over the eons, a stable balance emerged. Today, most planets and asteroids have settled into safe and predictable orbits. We have the inner and outer planets, the asteroid and Kuiper belt, and at the edge, the Oort cloud, a giant sphere of comets orbiting slowly in cold storage. We really don't want this balance to be disturbed. If another star came too close to us, its gravity would pull on everything in the solar system like a spoiled toddler, messing up the pleasant order of the planets and asteroids and comets. This isn't some imaginary danger. Some 70,000 years ago, a red dwarf-brown dwarf binary system passed through the Oort cloud and messed things up. It might even have sent a deadly onslaught of asteroids our way. But it could take 2 million years until those visitors from the Oort cloud arrive in the inner solar system. But there's a much bigger problem on the horizon. Gliese 710, a red dwarf with about half the mass of the Sun, is currently headed towards the solar system. In about 1 million years, it'll pass through the Oort cloud and become the brightest star in the night sky. A close flyby like this would unfold over hundreds of thousands of years, disrupting the orbits of millions of objects in the Oort cloud considerably. If we're unlucky, it will trigger a new period of planetary bombardment similar to the early solar system. The night sky could be filled with comets and asteroids raining down on the inner solar system. The larger ones could cause dinosaur-level mass extinctions and would be bad for the stock market. But it could get much worse. The galaxy is an intense place, and stars get close to each other regularly. So it is possible that a star could come much closer and not just pass us, but fly directly through the inner solar system. This would be very bad in the extreme. The chance of another star colliding with the Sun is astronomically unlikely, but that isn't what we're worried about. If another star were to pass by about as close as the Earth is from the Sun, it could easily eject the Earth from the solar system. The odds of such an event are estimated to be around 1 in 100,000 in the next 5 billion years. Small, but not absurdly so. As we discussed in another video, there seem to be billions of rogue planets doing their own thing in the galaxy, and this is one way to make them. So if this were to happen with an average red dwarf, what would happen on Earth? Kicking Earth out of the solar system. As the star enters the solar system, a small orangish dot appears in the sky that grows bigger and bigger for months, eventually becoming visible during the day. It would get bigger and much brighter than the moon. Too bright to look at directly. The night sky would be filled with an eerie red glow. After a few months, it would start shrinking again. But so would the sun. Over a few years, the sun slowly grows smaller in the sky, and with it warmth and light start to dissipate. All around the world, as the days turn dark, the final winter of humanity would begin. The polar ice caps begin to grow and spread, while plants shrivel and die. Forests freeze, and animals die in droves. As the Earth passes the orbit of Mars, the average surface temperature has plummeted to near -50 degrees Celsius. From space, Earth begins to look like an icy moon, the blue-green surface becoming the pale grey-white of death. As global infrastructure breaks down, people huddle together indoors, burning what they can for warmth as the temperature continues to drop, counting the days until they'll be out of food which no longer grows. Everybody living at the surface is living on borrowed time. By the time Earth reaches Jupiter's orbit, surface temperatures sink to -150 degrees Celsius, lower than the coldest ever recorded temperatures in Antarctica. Needless to say, by now, almost everyone is dead. Without the energy from sunlight to evaporate water, clouds don't form and the water cycle stops. The polar ice caps eventually touch at the equator and the oceans become covered in a thick layer of ice. As more and more of its heat leaks out, more water freezes onto the bottom of the ice sheet, the concentration of salt in the deep ocean grows, poisoning most animals that survived here. Although around hydrothermal vents, communities of extremophiles might adapt even to these circumstances. Deep below the surface, some bacteria would not notice much of any of this, as they're still kept warm by the radioactive decay of elements in the Earth's core. As the Earth reaches the orbit of Pluto and the Kuiper Belt, the Sun is still the brightest star in the sky, but it's one among many, with stars now visible during the day. The temperature is now barely 40 degrees Celsius above absolute zero, below the freezing temperature of the gases in the atmosphere. A weird spectacle, enjoyed by no one unfortunately, unfolds as the atmosphere turns into nitrogen and then oxygen snow. Over a few years, it's deposited into an icy 10-meter thick sheet all over the planet's surface, with only a thin whisper of gas remaining. The frozen corpses of flora and fauna are buried beneath them. As Earth leaves the solar system, it becomes a rogue planet, traveling alone through the dark, lifeless and in solitude. But weirdly enough, there is hope. Humanity would not be surprised by this potential extinction event. We'd notice it thousands of years in advance. There's not a lot we could do to stop a star, but we could prepare. Most of us would perish, but a few million could survive in huge artificial complexes powered by geothermal and nuclear energy, possibly even fusion if we can learn to use the ice around us for power. Here, humanity might survive for hundreds of thousands of years. At some point, we would become used to our circumstances, and new generations would watch documentaries in disbelief about the time we had our own star and could walk the surface of Earth. And at some point, we might decide to look for another home. If the Earth were lucky enough to pass by another star with a habitable planet, we could try to make a fresh start. Spaceflight, oddly enough, would become very easy without the atmosphere in the way. So it's not unthinkable that the last survivors would leave Earth behind and try again on a new planet around a new star. Maybe one day, thousands of years later, the descendants of humanity will tell legends about Earth's ancient past. Stories of our lost home, of a mysterious icy planet, floating alone and empty through the dark of space. Black holes can destroy everything, but can they be destroyed? What happens if we push physics to the absolute limit, maybe even breaking it and the universe in the process? Let's create a tiny black hole about the mass of our moon in the Kurzgesagt labs and try to rip it apart. Experiment 1. Nuke it. Big booms break things, so to set the mood, Let's explode the world's entire nuclear arsenal around our black hole. Boom! Black holes swallow whatever crosses their event horizon, matter and energy. And since E equals mc squared, all the energy that enters a black hole increases its mass. The mass of a black hole is proportional to its size, so as we nuke our tiny black hole, it just gets bigger and more massive. Experiment 2. Antimatter. Matter and antimatter annihilate each other. What will happen if we throw a moon's massive antimatter at it? Unfortunately, when an object enters a black hole, the black hole will completely delete its past identity, whether it's made of matter or of antimatter. Black holes only care about gravity, which only depends on the total mass energy of an object. And the mass of a particle is the same as its corresponding antiparticle, so throwing an anti-moon has the same effect as throwing a moon. The black hole just gets more massive. This deleting ability of black holes is pretty interesting. It means that despite their size and power, black holes are, in a way, similar to elementary particles. An elementary particle like an electron is an extremely simple object, fully specified by just 3 numbers, its mass, spin, and charge. And amazingly, the same is true for black holes. They have a mass, they can rotate, and carry an electric charge. Once a black hole forms, it doesn't matter if it comes from a collapsed star, an anti-star, or a banana, it will always be fully described by those 3 numbers, nothing else. But if a black hole is basically a weird particle, could we destroy it with an anti-black hole? Experiment 3. Anti-black hole. How exciting! A particle has the same mass as its corresponding antiparticle, but opposite charge. Since a black hole has mass and electric charge, its corresponding anti-black hole should have the same mass and opposite electric charge. What if we make them collide? Sadly, the charge will just add up and cancel out. So after the collision, we'll just get a new black hole twice as massive with no charge. Okay, we need to think bigger and stretch physics harder. Experiment 4. Destroy the event horizon. It's true that a black hole can carry spin and charge, but even for these crazy objects, there are limits. If the spin or the charge of a black hole becomes too large, something really weird will happen. The event horizon will dissolve. In a simplified way, we think of black holes as hiding a singularity inside, an infinitely compressed mass with such strong gravity that absolutely nothing can escape from its surroundings, not even light. This is why a black hole looks like a black sphere of nothingness. The event horizon is the outer edge of this ultimate prison. Cross it and you'll never be able to come back. But when a black hole rotates, it works a bit like a spinning washing machine. It's as if the rotation wants to repel nearby objects and push them out of the black hole, which doesn't happen because its gravity is so strong. But if the rotation gets too fast, this effect will win and the event horizon will disappear. Nearby objects won't be imprisoned forever anymore. The same thing happens with the electric charge. Make it too large and our ironclad jail will break open. If we manage to destroy the event horizon, the singularity would still be there, and objects would still naturally fall towards it. If you hit it, you would still die horribly and quickly. But the vicinity of the singularity won't be an inescapable prison anymore. You could get as close as you want and come back. This should count as destroying the black hole. Can we do it? Experiment 5. Overfeeding. All we have to do is to overcharge or overspin the black hole. We could do this by throwing objects with a small mass and a lot of charge or angular momentum so that the charge or spin increases faster than the mass. We have to overfeed the black hole until it reaches the point where it breaks open. However, whether you can actually do this is the subject of passionate argument among physicists. Think of a charged black hole. Equal charges repel each other, and the more of the same charges you squish together, the more they push back. So let's say that we have a negatively charged black hole and we want to overfeed it with electrons, for example, whose charge is far larger than its mass. The electrons will feel an electrostatic repulsion, and the more electrons we throw, the larger the negative charge of the black hole will be and the stronger the repulsion. But once we reach the upper limit, the electrostatic repulsion will be so strong that it won't allow any more electrons to come in. At this point, the black hole will refuse to be overfed. With the spin, it's similar. Once the black hole reaches its upper limit, it won't gobble more spin. But some scientists have discovered what looks like a loophole. If an instant before the black hole reaches the limit, we throw the right amount of matter in just the right way, it looks like we could actually overfeed it. Most scientists are skeptical, but let's give it a try anyway. The end? Breaking physics. There is a catch though. The event horizon of a black hole hides the singularity, so destroying the horizon would leave us with a naked singularity, one that is not hidden by an event horizon. And this poses a problem. It could mean the end of physics as we know it. There's a big dirty secret about black holes. Contrary to widespread belief, the singularity of a black hole is not really at its center. No, it's in the future of whatever crosses the horizon. Black holes warp the universe so drastically that at the event horizon, space and time switch their roles. Once you cross it, falling towards the center means going towards the future. That's why you can't escape. Stopping your fall and turning back would be just as impossible as stopping time and traveling to the past. So the singularity is actually in your future, not in front of you. And just like you can't see your own future, you won't see the singularity until you hit it. But you also can't hit something that's in your future, only sort of experience it, like you'll experience your next birthday when it happens. Singularities that are in the future are not a problem because we can't see them or interact with them. But a naked singularity would be in front of us for all of us to see. What would we see? Well, the whole point is that it's impossible to know. A singularity is a region of infinite gravity, and gravity is the bending of space-time. At a singularity, the bending is so radical that the fabric of space-time is literally broken. Space and time don't exist anymore. This means that you can't predict anything, since predicting means making a forecast about where and when something will happen. But where and when have lost their meaning. So we have an unpredictable thing with infinite gravity and therefore infinite energy. This means that anything could come out of it for no reason, from a pile of bananas to lost socks or a solar system. Predictability, causality, and physics as we know it would break down. We think that singularities should exist in nature because we can prove that under very general conditions, gravitational collapse leads to the formation of singularities. However, scientists think that nature forbids the formation of naked singularities. Something enforces the creation of an event horizon around them to prevent their insanity from infecting the rest of the universe. Without event horizons, physics may not make sense at all. So although black holes have been portrayed as the ultimate monsters of the universe, they may actually be the heroes that keep us safe from the madness of singularities. So if we do destroy the horizon, we might destroy the fundamental rules of the universe. You know what? Let's not do that. Conclusion: the safe option. As far as we know, there's just one safe method to destroy a black hole: wait. All black holes emit tiny particles, a phenomenon called Hawking radiation. This process causes them to slowly lose mass until they eventually evaporate, leaving behind no horizon and no naked singularity. The time it takes for a black hole to completely evaporate depends on its mass. For our mini black hole the size of a speck of dust, it will be about 10 to the power of 44 years, 10 billion trillion times the present age of the universe. So is it possible to destroy a black hole? Yes, we just have to wait. What would happen to you if a black hole the size of a coin suddenly appeared near you? Short answer, you'd die. Long answer, it depends. Is it a black hole with the mass of a coin, or is it as wide as a coin? Suppose a US nickel with a mass of about 5 grams magically collapsed into a black hole. This black hole would have a radius of 10 to the power of minus 30 meters. By comparison, a hydrogen atom is about 10 to the power of minus 11 meters. So the black hole compared to an atom is as small as an atom compared to the sun. Unimaginably small. And a small black hole would also have an unimaginably short lifetime to decay by Hawking radiation. It would radiate away what little mass it has in 10 to the power of minus 23 seconds. Its 5 grams of mass will be converted to 450 terajoules of energy, which will lead to an explosion roughly 3 times bigger than the atomic bombs dropped on Hiroshima and Nagasaki combined. In this case, you die. You also lose the coin. If the black hole had the diameter of a common coin, then it would be considerably more massive. In fact, a black hole with the diameter of a nickel would be slightly more massive than the Earth. It would have a surface gravity a billion times greater than our planet currently does. Its tidal forces on you would be so strong that they'd rip your individual cells apart. The black hole would consume you before you even realized what's happening. Although the laws of gravity are still the same, the phenomenon of gravity that you'd experience would be very different around such dense objects. The range of the gravitational attraction extends over the entire observable universe, with gravity getting weaker the farther away you are from something. On Earth right now, your head and your toes are approximately the same distance from the center of our planet. But if you stood on a nickel-sized black hole, your feet would be hundreds of times closer to the center, and the gravitational force would be tens of thousands of times as large as the force on your head and rip you into a billion pieces. But the black hole wouldn't stop with just you. The black hole is now a dominant gravitational piece of the Earth-Moon black hole of death system. You might think that the black hole would sink towards the center of the planet and consume it from the inside out. In fact, the Earth also moves up onto the black hole and begins to bob around as if it were orbiting the black hole, all while having swathes of mass eaten with each pass, which is much more creepy. As the Earth is eaten up from the inside, it collapses into a scattered disk of hot rock surrounding the black hole in a tight orbit. The black hole slowly doubles its mass by the time it's done feeding. The Moon's orbit is now highly elliptical. The effects on the solar system are awesome. In the biblical sense of awesome, which means terrifying. Tidal forces from the black hole would probably disrupt the near-Earth asteroids, maybe even parts of the asteroid belt, sending rocks careening through the solar system. Bombardment and impacts may become commonplace for the next few million years. The planets are slightly perturbed, but stay approximately in the same orbit. The black hole we used to call Earth will now continue on orbiting the Sun in the Earth's place. In this case, you also die. Nothing in the universe is static. In the Milky Way, billions of stars orbit the galactic center. Some, like our Sun, are pretty consistent, keeping a distance of around 30,000 light-years from the galactic center, completing an orbit every 230 million years. This dance is not an orderly ballet, more like a skating rink filled with drunk toddlers. This chaos makes the galaxy dangerous. Our solar neighborhood is constantly changing, with stars moving hundreds of kilometers every second. Only the vast distances between objects protect us from the dangers out there. But we might get unlucky in the future. At some point, we could encounter a star going supernova, or a massive object passing by and showering Earth with asteroids. If something like this were to happen, we would likely know thousands, if not millions of years in advance. But we still couldn't do much about it, unless we move our whole solar system out of the way. To move the solar system, we need a stellar engine, a megastructure used to steer a star through the galaxy. It's the kind of thing that might be built by an advanced civilization with Dyson sphere-level technology that's thinking about their future millions of years ahead of time. But how do we possibly move the hundreds of thousands of objects in the solar system? The good news is we can ignore all of that. We only need to move the Sun. All the other stuff is glued to it by gravity and will follow it wherever it decides to go. There are lots of ideas about what a stellar engine might look like and how it would work. We've picked two grounded in our current understanding of physics that could be built in theory. The simplest kind of stellar engine is the Skyhook thruster, a giant mirror. It works on the same principle as a rocket. Like rocket fuel, the photons released as solar radiation carry momentum. Not a lot, but a bit. For example, if an astronaut turned on a flashlight in space, it would push them backwards very, very slowly. A stellar engine will work a little better than a flashlight because the Sun produces a lot of photons. The basic idea of the Skyhook thruster is to reflect up to half of the solar radiation to create thrust and slowly push the Sun where we want it to go. In order for the Skyhook thruster to work, it must be kept in the same place, not orbiting the Sun. Although the Sun's gravity will try to pull it in, it would be supported by radiation pressure, which props the mirror up. This means the mirror would have to be very light, made of micron-thin reflecting foil from materials like aluminium alloys. The mirror's shape is important too. Enveloping the sun in a giant spherical shell wouldn't work because that would refocus light back to the sun, heating it up and creating all sorts of unpleasant problems. Instead, we use a parabola, which sends most of the photons around the sun and in the same direction, which maximizes thrust. To prevent accidentally burning or freezing Earth with too much or too little sunlight, the only safe place to build a Skyhook thruster is over the sun's poles. This means we can only move the sun vertically in the plane of the solar system and one direction in the Milky Way, which limits our travel options a bit. But that is basically it. For a civilization capable of building a Dyson sphere, this is a relatively simple endeavor. Not complicated, just very hard to build. At full throttle, the solar system could probably be moved by about 100 light-years over 230 million years. Over a few billion years, it gives us near complete control over the sun's orbit in the galaxy. But in the short term, this might not be fast enough to dodge a deadly supernova. That's why we thought we could do better. So we asked our astrophysicist friend if he could design a faster stellar engine for this video. He did, and wrote a paper about it that's been published in a peer-reviewed journal. You can find it in our sources document. We're going to call our new stellar engine the Kaplan thruster. It works a lot like a traditional rocket. Shoot exhaust one way to push yourself the other. It's a large space station platform powered by a Dyson sphere that gathers matter from the sun to power nuclear fusion. It shoots out a very fast jet of particles at nearly 1% the speed of light out of the solar system. A second jet pushes the sun along like a tugboat. The Kaplan thruster requires a lot of fuel, millions of tons per second. To gather this fuel, our thruster uses very large electromagnetic fields to funnel hydrogen and helium from the solar wind into the engine. The solar wind alone doesn't provide enough fuel though, and that's where the Dyson sphere comes in. Using its power, sunlight can be refocused to the surface of the sun. This heats small regions to extreme temperatures, lifting billions of tons of mass off the sun. This mass can be collected and separated into hydrogen and helium. The helium is burned explosively in thermonuclear fusion reactors. A jet of radioactive oxygen at a temperature of nearly 1 billion degrees is expelled and becomes our primary source of propulsion from our stellar engine. To prevent the engine from just crashing into the sun, it needs to balance itself. To do this, we accelerate the collected hydrogen with electromagnetic fields using particle accelerators and shoot a jet back at the sun. This balances the thruster and transfers the thrust of our engine back to the sun. In as little as 1 million years, this engine can move the sun by 50 light-years, more than enough to dodge a supernova. At full throttle, the solar system can be completely redirected in its galactic orbit in 10 million years. But wait, won't we use up the sun this way? Fortunately, the sun is so massive that even billions of tons of material will barely scratch the surface. In fact, this megastructure will actually extend our sun's life, since lower mass stars burn slower, keeping the solar system inhabitable for many more billions of years. With a Kaplan thruster, we could turn the entire solar system into our spaceship. For example, by orbiting backwards in the galaxy and colonizing hundreds or thousands of stars as we pass by them. It may even be possible to escape the galaxy entirely and expand beyond the Milky Way. Stellar engines are the kind of machines built by civilizations thinking not in terms of years or decades, but eons. Since we know that our sun will die one day, a stellar engine could allow the far future descendants of humans to travel to other stars without ever having to venture into the terrifying dark abyss of interstellar space. Until we build a stellar engine, we're adrift and subject to the whims of the galactic sea. We may not like where it leads us. Maybe our descendants will set sail and become an interstellar species for millions of years to come. This was our last video for the year 12,019 of the human era. And what a year it was. So much stuff happened everywhere, to so many different people. Calendars and holidays are just imaginary, but they help us to cut our lives into pieces that our brains can handle. We're leaving 12,019 behind with a weird mixture of disillusion and hope. The world is screwed up, but we can fix it. In a few days, this year will be over, and we'll get to try again. Thank you for watching our videos, and for sticking around for so many years. See you all in 12,020. Supernovae are the most powerful explosions in the universe, unleashing enough energy to outshine galaxies. We have no real metaphor for their power. If the sun were to magically go supernova, it would feel like you were being hit by the energy of a nuclear explosion every second for weeks. While supernovae are the engines of creation, forging the elements that enable life, they also burn sterile whole regions of galaxies. So what would happen if one hit Earth? There are, roughly speaking, two ways to make a supernova. Either the core of a massive star implodes, or, less common, a white dwarf gains mass to the point where it ignites explosive nuclear fusion. The outcome is the same, a supernova explosion. When we think of an explosion on Earth, we think of something that happens fast and ends. But a supernova is more like a volcanic eruption followed by a tsunami. At first, there's a colorful ball of hot, expanding gas, creating a spectacular cloud that will shine for about a month. But then, it doesn't stop. Hot and dangerous gas rushes outwards at speeds of 10,000 kilometers a second through the near vacuum of space, sweeping up the sparse gas of the galaxy. This wall of gas expands for tens of thousands of years and will eventually span up to dozens of light years until it finally cools off and disperses its substance back into the galaxy. So what if this star tsunami hits us? Well, the damage depends on how far away it is. Stage 1, thousands of light years away. Humans have witnessed dozens of supernovae, but all of them were thousands of light years away. They appeared as new stars, some outshining the moon, twinkling for a few weeks, and disappearing. Aside from looking very pretty at this distance, they don't do much to us. Stage 2, 300 light years away. Things begin to get a bit icky once a supernova occurs around 300 light years away. We can expect one this close to us every few million years. A single star giving the night sky an eerie glow like twilight. And while this is far enough away and dim enough to not do harm to us, they can affect the Earth. At these distances, it's like being hit by the last weak waves of the star tsunami. Not strong enough to do real damage, but still noticeable. In fact, we know that over the past 10 million years, multiple supernovae have struck Earth from these distances because we can find radioactive isotopes of iron deep in the rocks and sediments at the bottom of the ocean. Amazingly, these supernovae around the solar system have cleared a 1,000 light-year wide pocket of space that's called the local bubble. They blew away the interstellar gas and dust, creating a lumpy wall of gas that's now a cradle for star formation. Stage 3, 150 light-years away. Once a supernova happens much closer than 300 light-years, we're approaching the zone where it does real damage. Stars have extremely powerful magnetic fields. When they die, the tsunami of dead star actually retains a lot of this magnetic energy woven through the shockwave that expands outwards. In this highly magnetized cloud, we get conditions like in a huge particle accelerator that's accelerating charged particles like protons, nuclei, and electrons to immense speeds. Which means we have an expanding cloud that is shooting deadly radiation in all directions long after the bright light from the initial explosion has faded away. If a supernova happens too close by, waves of these cosmic rays will wash over the solar system for thousands of years. While we're mostly protected on Earth's surface by the atmosphere and ozone layer, the influx of extra radiation will still increase cancer and mutation rates. Not enough to cause a mass extinction, but it will be noticeable. Spaceflight would become impossible in the solar system as astronauts wouldn't survive the waves of radiation for long. We don't know exactly how bad this would be, but a supernova that is close enough may trap our species on Earth for generations, maybe thousands of years. It only gets worse from here. Stage 4, closer than 100 light-years. Within 100 light-years, things get bad, as a supernova disrupts our climate in ways that we don't fully understand yet. There are a few unpleasant things happening all one after another. First, the high-energy photons arrive from the explosion, followed by many decades of radiation from the radioactive tsunami, both of which seriously damage the ozone layer, Earth's shield against harmful radiation. The ozone layer absorbs ultraviolet radiation by breaking apart ozone, O3, into O2 and a free oxygen atom, which later reforms back into another ozone molecule. But the supernova radiation breaks up nitrogen molecules that gobble up the free oxygen, breaking the cycle and depleting the ozone layer quickly. Without a radiation shield, everybody living on the surface is exposed to very high levels of UV radiation from our sun. Cancer rates would skyrocket, and just going outside during the day could be life-threatening. The extra radiation would also kill a lot, if not most, of the plankton in the oceans that live near the surface and are the basis for the marine food chains, leading to a mass extinction. Worse still, supernova radiation would ionize gas in the atmosphere, which means that it would punch through molecules and knock electrons off nuclei, leaving them charged. These charged nuclei then act as seeds for water vapor to gather and form massive global clouds. In the worst case, they would reflect enough sunlight to trigger an ice age. In fact, it's thought that the ice age 2.5 million years ago was caused by a supernova. Some scientists even think that a supernova about 60 light-years away might have been the cause of the Devonian mass extinction 350 million years ago. But wait, there's more. The electrons punched free by the radiation form enormous electric avalanches, or in other words, lightning. Earth is hit by some of the worst thunderstorms in millions of years. The intense lightning causes global wildfires that consume forests and crops, devastate cities, disrupt our electrical grids and global supply chains, all while a decimated ozone layer leaks deadly radiation. While in the past the ecosystem may have bounced back from a nearby supernova after a few thousand or million years, there's no guarantee modern civilization can take a hit of this magnitude. We would face food shortages, skyrocketing prices and wars as nations struggle to not be consumed by chaos. So a supernova this close would at the very least do significant damage for hundreds or thousands of years, if not end our modern civilization, and with it millions or even billions of lives. Still, humanity would likely survive and could recover. Stage 5, closer than 25 light-years. A supernova closer than 25 light-years means that we're in its kill radius, where a mass extinction is all but guaranteed. Probably about half of the ozone layer would be destroyed, and massive climatic disruption on a scale we've never witnessed would ravage Earth. Entire ecosystems would swiftly be wiped out by radiation as global wildfires envelop the planet. All the things described before happen, but way more intensely and much faster. A few people might survive for years in bunkers if they have food supplies, but the world they return to will be devastated and hostile to life for hundreds of thousands of years. Human extinction is extremely likely. The final stage, 4 light-years. Being any closer to a supernova is very unlikely because space is big, but the effects would be extreme. Even from 4 light-years away, the distance to Alpha Centauri, a supernova would be almost as bright as the sun in the sky. While casting 2 shadows could be fun for a few hours, within days the Earth's surface gets as hot as a sauna, baking the surface for weeks until the explosion fades. The surface of Earth burns, scoured of life. Even the oceans aren't safe. The massive amount of radiation that follows burns away the ozone layer, killing everything that sees sunlight. It would be the largest extinction event in history, reducing life to a few survivors in the deep sea and critters in the deep soil. Life basically has to start over. Conclusion: how worried do you need to be? So, should you worry? No. Fortunately, there are only a handful of stars that may explode within 1,000 light-years of Earth, and none are close enough to be a serious threat. Even better, these stars will probably not go supernova for many millions of years. So you are safe. But there's no guarantee for the far future. As stars orbit the galaxy, our descendants may find themselves dangerously close to a supernova. But by then, a far more advanced and wiser humanity will hopefully be able to just move out of the way. In any case, you can sleep well tonight under the beautiful night sky. Here in the Kurzgesagt labs, we test very important ideas to see what happens when you blow things up or play with black holes. Many of you suggested that we look into an idea that sounds reasonable: shooting nuclear waste into space. It's one of those concepts that seems like an easy fix for one of the main problems with nuclear energy. But it turns out this idea is not just bad, but horribly bad, and it gets worse the longer you think about it. Why is that? What is nuclear waste? Nuclear waste is a fuzzy term and comes in categories which vary from country to country. But in general, there are three broad levels. 90% is low-level nuclear waste, tools, gloves, or trash used at a nuclear facility that could be weakly contaminated with some short-lived radioactivity. This stuff is generally safe for normal disposal. 7% is intermediate-level nuclear waste, mostly materials that have been in close proximity to a reactor core long enough to become dangerously radioactive. With proper handling, it's either safely buried or melted down and mixed into glass or concrete and stored deep underground. So 97% of nuclear waste is similar to toxic byproducts from other industries. Not great, not terrible. We can handle it. The remaining 3% is where our problems begin. High-level nuclear waste is very concentrated spent fuel taken out of a reactor core. Formerly uranium, it's now made of various dangerous and often highly radioactive elements. As a bonus, it's also incredibly hot and not easy to handle at all. This is what we want to shoot into space. All in all, around 440 active nuclear reactors create about 11,000 tons of high-level nuclear waste each year. Since 1954, we've accumulated 400,000 tons of dangerous radioactive waste. Most countries are dealing with it by not dealing with it and kicking the can towards the future. Great, so let's launch it into space. According to scientists, space is big, and nobody lives there, so it seems perfect for yeeting away this mess. There are a few tiny problems though. Problem 1, stuff ain't cheap. Even though spaceflight is getting more affordable, it's still extremely expensive. Just to get something into low Earth orbit costs on average about $4,000 per kilogram. Putting that into perspective, it costs about $1,600 to mine, separate and fabricate 1 kilogram of nuclear fuel, so launching waste into space has suddenly made nuclear fuel for reactors way more expensive and greatly increased the cost of the electricity they produce. To launch 1 reactor's worth of nuclear waste would cost at least $100 million per year. To deal with all the 440 operational nuclear power plants' high-level nuclear waste would cost some $44 billion per year for space launch before packaging, transport and security costs are added. Okay, let's pretend we don't care. Currently, we couldn't shoot all the nuclear waste into space even if we wanted to. There just aren't enough rockets. In 2021, we saw a record 135 launches into space. If we repurposed each of those rockets and filled them all with nuclear waste, the total amount that could be lifted into a low Earth orbit, which is the closest orbit above the atmosphere, is nearly 800 tons. We'd need at least 14 times more rockets to handle just today's nuclear waste, let alone get rid of the hundreds of thousands of tons in temporary storage. We would need to create entire new space industries to keep up with the demand for giant, toxic space trash trucks. And it gets worse. Problem 2, space is hard. We only made the calculation for low Earth orbit, where we send most of our rockets and satellites. Littering the space around Earth with thousands of casks of spent nuclear fuel would be a nightmare for space junk management and satellite collision avoidance. Worse still, at this altitude, there's still a little bit of atmosphere causing a tiny bit of drag, so we might have nuclear waste raining down from space within just a few years. Experts would call this a huge problem. Clearly, we have to launch our waste further. If we wanted to send it to, perhaps, the moon, we either need way more rockets or we need to build much bigger ones, making it even more expensive. A single Saturn V, the rocket used by the Apollo program, which cost around $1.5 billion adjusted for inflation per launch, could get about 43.5 tons from the Earth to the Moon. So we'd need about 260 Saturn V rocket launches every year. And of course, using the moon as target practice for nuclear waste-tipped rockets kind of makes a huge mess. So maybe don't aim for anything. Space is empty. Do we really need a target? Shooting waste in any random direction is, you guessed it, also a bad idea. Orbits are loops, which means they have a tendency to come back to where they started. Put enough in the sky in random directions, and you'll get one back eventually. So we'd want to launch our nuclear waste deep into space, which means we need even bigger rockets that would be even more expensive. Not that we would be completely safe then. Earth might run into these interplanetary caskets at some time in the far future and experience a pretty meteor shower made from radioactive dust. Okay, how about we shoot it into the sun? Ironically, the sun is pretty hard to hit. While the sun has very strong gravity, everything on Earth is moving with respect to the sun, including the rockets that we launch, meaning a rocket would have to cancel out all the orbital motion it has around the sun so it can stop orbiting and fall in. Because of this, it's actually easier to launch a rocket entirely out of the solar system than it is to launch it into the sun. But to do either of these things, we need even bigger rockets, probably the biggest we've ever built. Nothing works. The thing is, it gets even worse. Problem 3. Rockets go brrr. Rocket engineering has taken huge steps since the Apollo era. We've made them relatively safe. We've mostly replaced the toxic explosive cancer fuels of the past decades with much saner mixes of liquid oxygen and hydrogen or kerosene. The newest designs even land themselves so that they can be reused. And yet, out of the 146 launches in 2021, there were 11 failures, which means that a sizable number of our rockets carrying high-level radioactive waste would be exploding on the launch pad, or in the worst case, disassembling at high altitude or crashing from hypersonic speeds. Each failure would be at least equivalent to a mini Chernobyl, but instead of being contained under a slab of concrete, spread throughout the atmosphere. Radioactive particles could make their way to faraway places by riding on the winds. Most would fall into the ocean, but some would land on the inhabited parts of the world. They could cover farmlands and get concentrated into our food or enter our water supply. Which is, well, bad. Imagine regular large-scale nuclear disasters happening. People wouldn't be happy. Conclusion and opinion part. Nuclear waste is scary, but the fear of it and horrible ideas like shooting it into space reveals how bad we are at understanding risk, because the largest amounts of radioactive elements like uranium and radon are actually released by coal. Burning millions of tons of coal each year leaves ash as a waste product that includes about 36,000 tons of radioactive materials. Less radioactive than high-level nuclear waste, but there's also a lot more of it, and it's handled way less carefully. Some of this ash is caught by filters, but most is simply pushed back into leaky mines, shoved into piles exposed to the wind, or poured into ponds that regularly spill into rivers and lakes. Living within 1.6 kilometers of an ash pile increases your cancer risk up to 2,000 times over the acceptable limit. And this is on top of other toxic chemicals like heavy metals and, of course, their massive CO2 emissions. And yet, while nuclear energy is flawed and its current form may only be a transitory technology, nuclear power plants are a harder sell than coal. Nuclear waste and the lack of willingness to deal with it are a real issue. It's not insurmountable, though. There are good methods to handle it, like burying it deep underground or reprocessing some of it into new fuel. But however we ultimately deal with this issue, we hope one thing is clear. Shooting nuclear waste into space is one of the worst ideas ever. The vast majority of the cosmos is voids. Gigantic, unfathomably large spaces of empty nothingness. Bubbles of eternal night stretching hundreds of millions of light years, almost entirely devoid of galaxies, stars, or light. The loneliest places in existence. Voids are not just the absence of stuff, but weird worlds of darkness that are growing, drifting, colliding, and merging with each other. Inside them, space itself is stretched violently, and it's almost impossible to enter them. Simply put, voids are weird and scary, but they sculpt the entire universe and may ultimately decide its fate. Today, we know of over 8,000 voids and supervoids, and we keep discovering more. No matter how large a cluster or supercluster of galaxies gets, there always seems to be an even larger void nearby. Let's jump off the cosmic cliff and drop into the heart of cosmic nothingness. The loneliest place in the universe. You're zooming away from Earth at thousands of times the speed of light, leaving our solar system and our solar neighborhood behind. Now we see the entire Milky Way with its 200 billion stars and dozens of dwarf galaxies zipping around it. 2.5 million light-years away on a collision course is giant Andromeda and its own swarm of satellite galaxies. We're now moving 1 million times faster than the speed of light, seeing the local group of over 50 galaxies woven together by gravity, rivers of gas, and invisible scaffolds of dark matter. This is our pocket of the universe, 10 million light-years across. No human will ever leave it. Except for you, apparently. As we zoom away even faster, we see the Virgo supercluster, a colossal wall of more than 2,000 galaxies spread over roughly 100 million light-years. Careful now, you're right on the edge of the cosmic cliff where the true deep darkness begins. The local void, a gigantic empty bubble 200 million light-years across. If it was a bright thing and not absolute darkness, it would fill 40% of the night sky we see from Earth. All around us are dozens of such superclusters and gigantic voids filled with suffocating emptiness. You're now traveling towards the greatest and emptiest nothing in existence, right into the center of the Boötes supervoid, a cosmic desert around 300 million light-years wide. So gigantic it should contain thousands of galaxies. But instead, what do you see? You're surrounded by perfect darkness, the most absolute blackness the human mind can conceive. There is no up or down, no motion, nothing to orient yourself. There's not a single sign that the outside universe even exists. It's an inescapable prison, and this isn't some exotic corner of the cosmos. This is how the vast majority of the universe feels to human eyes. Just silent blackness without any movement. Everywhere, forever. Although there is something mysterious hiding in the dark, faint tendrils of dark matter, penetrating into the void like cosmic lichen. A miniature echo of the much larger forest of dark matter filaments that forms the scaffold of galaxies and galaxy clusters outside the void. And at their tips, we find faint bluish specks in the ocean of darkness. Void galaxies, lonely fireflies, unable to light up the night. The rarest galaxies we know, very isolated, very lonely. A universe of bubbles. Before we could look deep into space, astronomers thought we lived in a uniform cosmos with galaxies spread out evenly. But instead, we found that galaxies, cosmic gas, and dark matter were arranged into a vast cosmic web, a recurring pattern of sheets and filaments organized around enormous empty gaps, meeting at dense knots with galaxy clusters and superclusters. But this structure is not static. It just seems to be because the distances between galaxies are so incredibly vast. In reality, galaxies shoot through space at speeds of millions of kilometers per hour. They're on collision courses, orbiting each other, moving towards the center of larger galaxy clusters millions of light-years away. But they always seem to stick to the rims of voids like reflections of light on soap bubbles, which is kind of weird. If they're this dynamic, shouldn't a galaxy shoot into a void occasionally? Well, voids are actually extremely hard to enter for galaxies from the outside, at least naturally, because gravity becomes weird at their edges and even weirder deeper inside them. If you didn't know better, you might think voids spit out anything trying to get inside, pushing galaxies to the edge. The way gravity works is that everything with mass in the universe attracts every other thing with mass. And since there's almost no mass inside, the cosmic web of galaxy superclusters on their edges are pulling things out of voids. The emptier a void is, the harder gravity is pulling on what remains. It's really like a tug-of-war where one side isn't even trying. Over time, voids are really only getting even emptier and the walls and knots around them denser and brighter. Would it be hard to fly into a cosmic void with a spaceship? Well, not technically. The hardest part is escaping the gravity of your home galaxy. It also doesn't make much sense because what exactly do you want to visit inside a void? It makes sense to fly into a void if you want to hide, like really, really hide. But what cosmic horror would be scary enough for a civilization to try to escape into a cosmic void? Galaxies in the crowded cluster regions like our Milky Way are very active. Since its neighbor's gravity tugs and pulls at it, they collide and merge. Void galaxies are so isolated that they're aging in slow motion. They tend to be smaller, bluer, and full of gas, birthing new stars slower and calmer. So void galaxies could be the last places that will stay habitable in our dying universe. The last star in the universe will likely be born here. So maybe in 100 trillion years or so, a desperate alien race will embark on an impossible journey to stretch their existence just a bit longer inside a void galaxy. There's one more thing that makes voids unique places: dark energy, the mysterious force that most scientists think is accelerating the expansion of the universe and will ultimately cause its demise. We can't see dark energy do anything inside our galaxy or inside clusters because there's too much stuff putting things together via gravity, but we can see its effects inside voids. Here, dark energy blows up the bubbles of nothing. This is where the acceleration of cosmic expansion becomes visible. As voids are getting larger and larger, they're breaking the structure of the universe. The beautiful galaxy filaments are slowly being ripped apart. As the emptiness encroaches, walls of thousands of galaxies are thinned out and pulled towards the edges, attracted by much denser regions at the margins, giving space to the emptiness of two void bubbles becoming one. In the far, far future, supervoids will take over the observable universe, crushing clusters and expanding further and further until the entire observable universe is nothing more than a gigantic void of nothingness, the loneliest place in existence.